Welcome curious minds and sleepy thinkers. Settle in, find a comfortable stillness, and let your breath slow as you watch the last embers of the day fade. We are here together not to solve great mysteries, but simply to sit with them, to hold them gently in our minds, and to let them soothe us with their vastness. Tonight, our journey begins not out among the stars, but right here at our feet on our beautiful blue planet. We will start with what we know, and from there we will quietly drift outward into the great unknown. Imagine our solar system as a great cosmic mobile with the sun at its radiant center. The planets, each a unique jewel, are suspended in a delicate balance, orbiting in a never-ending dance. But among these, our Earth holds a very special, almost magical place. We will explore its gentle dance, its quiet strength, and the subtle forces that conspire to make it a haven of life. This prime location, this perfectly measured distance from our sun, places Earth squarely within what scientists lovingly call the habitable zone. It's a sweet spot, a cosmic Goldilocks zone where conditions are just right for liquid water to exist on a planet's surface. Think of it as a cozy armchair, perfectly positioned by a warm, crackling fireplace. Too close, and the heat would be unbearable, scorching everything, boiling away the very essence of life. Our neighboring Venus, cloaked in a thick toxic atmosphere, experiences a runaway greenhouse effect, trapping heat and baking its surface at temperatures hot enough to melt lead. It's a stark reminder of what happens when a planet veers too close to the sun's fiery embrace. Our own Mercury, the closest planet to the sun, is a desolate, cratered world, swinging between unimaginable heat on its sun-baked side and frigid cold in its perpetual shadow. These are worlds of extremes where the delicate balance needed for liquid water is simply impossible. Now imagine if we were placed too far from that comforting cosmic fire. If Earth had drifted further out beyond the orbit of Mars, we might resemble the frigid ice giants of the outer solar system, Uranus and Neptune, or even distant Pluto, a world perpetually locked in a deep freeze. Our beautiful oceans would be solid blocks of ice, and the very chemical reactions that spark and sustain life would grind to a halt. The subtle warmth that permeates our planet, allowing water to flow freely to sculpt landscapes and nourish life, would be entirely absent. We would be a silent, crystalline world, forever locked in winter's grip. Our planet's average distance of about 93 million miles from the sun is not merely a number. It is a cosmic blessing, a precisely tuned dial that sets the stage for everything that thrives here. This prime location fosters a temperate climate that has supported life for billions of years, a testament to the elegant precision of our universe. This perfect placement allows for the most precious ingredient of all liquid water. Imagine water as the very elixir of life, a magical solvent and medium, where the intricate complex organic reactions, crucial for life's genesis and continuation, can take place. It is a silent, ancient observer flowing through the planet's veins, collecting in vast, shimmering oceans and whispering through the soil. From the smallest microbe to the largest whale water is the fundamental cradle of existence. It is not merely a substance. It is a profound and ancient character in the unfolding drama of life. This liquid state, this constant cycle of evaporation, condensation, and precipitation shapes our planet's climate, erodes mountains, carves canyons, and provides the fundamental medium for biological processes that are still in many ways beyond our complete understanding. The ability of water to exist in all three phases, solid, liquid, and gas, within our planet's temperature range is a unique gift, driving intricate weather patterns and sustaining diverse ecosystems. Our planet's journey around the sun, what we call an orbit, is another marvel of cosmic choreography. Earth completes one revolution in approximately 365 days, a rhythm that creates the familiar cycle of seasons that has so profoundly shaped the evolution of life on our planet. Imagine this as a grand cosmic dance, a slow, deliberate waltz around our star. This annual journey, coupled with Earth's slight axial tilt, dictates the changing patterns of light and warmth, prompting plants to blossom and shed leaves, animals to migrate, and ecosystems to adapt in a continuous vibrant flow. This rhythmic ebb and flow has sculpted the very fabric of life, imprinting itself on the genetic code of every living thing. And in this dance, Earth is not alone. It performs with its singular large moon, a silent partner whose gravitational pull adds another layer of complexity and stability to our world. This cosmic ballet, this unique partnership, makes Earth a truly singular world within the grand expanse of the solar system. When we consider the sheer scale of our solar system, Earth sits in a rather modest position in terms of size. Imagine a cosmic family portrait. Among the 8 planets that gracefully orbit our Sun, Earth is the 5th largest. We are not the giants, nor are we the smallest, but rather a comfortable middle child. We are dwarfed by the magnificent gas giants like Jupiter and Saturn, colossal spheres of swirling hydrogen and helium so vast that Jupiter alone could encapsulate Earth more than 1,000 times. Imagine stacking more than 1,000 blue marble Earths inside that immense swirling vortex of Jupiter's clouds. And even the ice giants, Neptune and Uranus, though further out and less dense, still cast a much larger shadow than our humble home. They are the behemoths, the titans of our solar system, their immense gravitational fields orchestrating the orbits of countless moons and creating magnificent ring systems. Yet when we look at our nearer neighbors, our closest cosmic kin Earth stands out as remarkably substantial. Venus, often called our sister planet, is only slightly smaller, with a surface area approximately 90% that of Earth's. Imagine 2 apples, one just a tiny bit smaller than the other. That's the relative scale of Earth and Venus. They are surprisingly similar in overall dimension, despite their wildly different environments. Mars, on the other hand, is significantly smaller with a diameter just over half of Earth's. Picture a golf ball next to a baseball, and you get a sense of the scale difference. This makes Mars akin to a smaller sibling in our cosmic family, a world that once held the promise of liquid water, but now appears to be a desolate, frozen desert. Despite its modest size, Earth's true marvel lies in its diverse and dynamic geology. Imagine a planet constantly in motion, a living, breathing canvas being sculpted by unseen forces. From its towering mountain ranges that scrape the sky, born from the slow, relentless collision of continental plates, to its mysterious deep oceans that plunge into abyssal trenches. Earth is a place of immense complexity and wonder. Continents drift across its surface at a glacial pace, reforming over millions of years, opening and closing vast ocean basins. Volcanoes erupt, spewing molten rock and gases, reshaping the land and influencing the atmosphere. This geological activity is not just a passive process. It is a vital engine cycling carbon through the carbon silicate cycle, a slow, deep breath of the planet that regulates the atmosphere and climate over vast geological timescales. This continuous reshaping fosters incredible biodiversity, creating a constantly evolving tapestry of habitats where life can thrive and adapt. The sheer dynamism of Earth's surface far outweighs what its size alone might suggest, painting a picture of a world constantly reinventing itself, a testament to the powerful forces at play beneath its crust. Now let's turn our attention to the delicate yet powerful confluence of unique features that combine to make Earth a truly remarkable feat of habitability, creating the perfect conditions for life as we know it. At the forefront, as we've already whispered, is Earth's precise distance from the Sun, placing it squarely in the habitable zone. This prime real estate allows temperatures to exist where liquid water can persist on its surface. Water, the very elixir of life, acts as a solvent and a medium, where the intricate and complex organic reactions so utterly crucial for life's existence can take place. Imagine it as the fundamental ingredient in a cosmic recipe, without which no other ingredient could truly come alive. It flows, it dissolves, it transports, and it sculpts. making it the silent architect of all living things. Beyond its fortuitous placement, Earth's atmosphere is a truly special blend of gases. Imagine it as a shimmering multi-layered veil, rich in nitrogen, around 78%, and oxygen, approximately 21%, with trace amounts of other gases like argon and carbon dioxide. This unique composition stands in stark contrast to the toxic and dense carbon dioxide atmospheres of Venus and Mars, or the hydrogen and helium-dominated atmospheres of the gas giants like Jupiter and Saturn. Our atmosphere is not merely a mixture. It is a meticulously balanced respiratory system for the entire planet, supporting the vast range of complex biological processes, including photosynthesis, which is absolutely critical for life as we know it. This process, where sunlight is transformed into energy, forms the very base of our planet's food chain, a continuous silent hum of life-giving activity. Within this atmospheric tapestry, a particular layer, the ozone layer in the stratosphere, acts as a crucial barrier. Picture it as a delicate, invisible shield, constantly absorbing the sun's harmful ultraviolet UV radiation. Without this protective blanket, the surface of Earth would be bathed in radiation too intense for complex life to survive. It's a silent sentinel, working tirelessly to preserve the fragile balance. Furthermore, our atmosphere also cleverly facilitates the greenhouse effect, a natural process that gently traps heat and maintains the planet's surface at life-supporting temperatures. It's like a cozy, perfectly adjusted blanket, keeping us warm enough without overheating. In contrast, Venus's incredibly thick atmosphere leads to a runaway greenhouse effect, making it the hottest planet in our solar system, a fiery inferno where nothing can survive. Mars's thin atmosphere, on the other hand, offers scant protection from the sun's radiation and the extreme cold of space, leaving its surface desolate and barren. This delicate balance of gases protection and temperature regulation is truly a cornerstone of Earth's unique capacity to harbor life. Now let's dive deeper into another unseen guardian, Earth's magnetic field. Imagine it as a vast, invisible shield generated by the tumultuous churning of molten iron in our planet's liquid outer core. This powerful shield extends far into space, forming a protective bubble around our planet, known as the magnetosphere. It acts like a giant cosmic deflector, pushing aside the relentless solar wind, a continuous stream of charged particles emanating from the sun. Without this powerful protective embrace, Earth's atmosphere could have been gradually stripped away over time, much like what is believed to have happened to Mars, rendering our planet barren and exposed. During intense solar storms, when the sun releases an even higher flux of these charged particles, the magnetosphere's role becomes even more evident. It heroically channels some of these particles toward our planet's poles, creating the breathtaking natural light displays we know as auroras, the northern and southern lights. These ethereal curtains of light are not just beautiful, they are a visible testament to the invisible shield protecting us. Lastly, Earth's dynamic geological activity plays a truly pivotal role in recycling carbon through the vital carbon silicate cycle. Imagine this as the planet's slow, steady breath regulating the atmosphere and climate over immense geological timescales. Tectonic movements, the grand agonizingly slow dance of Earth's continental plates, have continuously shaped the continents, creating new landmasses, uplifting towering mountains, and forming vast ocean basins. This dynamic surface fosters incredible biodiversity, constantly creating new niches and environments where life can evolve and adapt. All these factors, our perfect distance, our unique atmosphere with its ozone shield, our powerful magnetic field, and our dynamic geology, combine in a symphony of natural forces to make Earth a truly unique haven for life in the vast, silent expanse of space. It's a delicate, intricate ballet where each component plays an indispensable part, allowing the gentle hum of life to continue uninterrupted for billions of years. It's a system of such finely tuned balance that it invites deep wonder, a profound sense of gratitude for this cosmic gift we call home. Now, let's turn our gaze to our constant companion in the night sky, our singular natural satellite, the Moon. Imagine it as a faithful dance partner circling Earth with profound influence, subtly shaping our planet in ways we often take for granted. The Moon, the fifth largest satellite in our solar system, plays a significant role in orchestrating Earth's natural phenomena. Its most apparent and widely recognized impact is its gravitational pull, which is primarily responsible for the rhythmic rise and fall of ocean tides across the planet. Picture the Moon's gravity as an invisible hand, gently pulling on Earth's oceans, causing them to bulge out both toward and away from the Moon. These bulges create the high tides, while the areas in between experience low tides. This continuous rhythmic motion of water has profound implications for marine life, influencing feeding patterns, breeding cycles, and the very structure of coastal ecosystems. It also dictates the rhythm of human maritime activities, from fishing to shipping, integrating the Moon's silent presence into our daily lives. Beyond the tides, the Moon plays an even more profound, yet often unseen role. It stabilizes Earth's axial tilt. Imagine Earth spinning like a top with a slight tilt to its axis. This tilt is precisely what gives us our changing seasons. Without the Moon's powerful stabilizing gravitational influence, Earth's axial tilt might experience erratic, unpredictable shifts. Picture a wobbling top, unstable and chaotic. Such drastic changes in tilt could lead to extreme and rapid climate shifts over relatively short geological timespans, swinging from ice ages to scorching deserts, making it incredibly difficult for complex life to adapt and flourish. The Moon acts as a steadying hand, a gravitational anchor, ensuring a relatively stable climate over eons, allowing life to evolve and diversify in a predictable environment. It's a silent guardian, ensuring the long-term stability necessary for life's deep journey. The Moon's presence also subtly contributes to Earth's rotation speed. Imagine a gentle friction, a slow continuous drag. Tidal friction caused by the Moon's gravitational pull on Earth's oceans and solid body is gradually slowing our planet's rotation imperceptibly, lengthening the day over immense periods of geological time. Billions of years ago, a day on Earth was much shorter, perhaps only a few hours long. This slow, steady lengthening of the day is another testament to the Moon's profound and ongoing influence on our world. Historically, the Moon has been far more than a celestial body. It has been a powerful catalyst for scientific curiosity and exploration. Since ancient times, humans have gazed up at its luminous face, tracking its phases and weaving its mystery into their narratives. This early stargazing laid the groundwork for astronomy, inspiring some of the earliest scientific inquiries. But its influence extends beyond the purely scientific. The Moon has played a truly significant role in the cultural and spiritual lives of civilizations throughout human history. From ancient myths and folklore to modern poetry and art, its ethereal presence has inspired awe, reverence, and imagination. It has been a symbol of fertility, of cycles of mystery, and of unreachable beauty. Its influence extends far beyond the physical, permeating the very fabric of human thought, art, and aspiration. It is an intrinsic part of how Earth is perceived and experienced, a luminous counterpoint to our blue world, a constant reminder of the wider cosmos beyond our immediate reach. The Moon is not just a rock in space. It is a profound echo in the human soul, a symbol of our longing to reach beyond ourselves. Its quiet, luminous presence in our night sky continues to inspire us, reminding us that even our closest cosmic neighbor holds deep secrets and plays an integral part in the story of our planet. The Moon is a silent witness to our history, a gentle guide in our exploration of the cosmos, and a constant invitation to look up and wonder. Now, as we gently pull back from the intimate dance of Earth and its Moon, let us quietly expand our view, drifting further outward, past the familiar orbits, to whisper about the grand architecture of our solar system and the first faint hints of what lies beyond its immediate embrace. Our home, this beautiful blue marble, is nestled within a much larger cosmic structure, a vast and intricate system governed by the immense gravitational pull of a single star, our Sun. Imagine our solar system not just as a collection of individual planets, but as a giant, swirling mobile, an elaborate clockwork mechanism in perpetual motion with the Sun as its powerful magnetic heart, holding everything together in a delicate cosmic embrace. The Sun, a middle-aged yellow dwarf star, is the undisputed sovereign of this realm. Its sheer mass is staggering. It contains about 99.8% of the total mass of the entire system. Picture all the planets, all the moons, all the asteroids and comets combined. Their combined weight barely registers compared to the Sun's colossal bulk. This immense gravitational dominance is the fundamental principle that keeps all the solar system's constituents in orbit around it, ensuring that none of these celestial wanderers stray too far into the lonely void of interstellar space or collide catastrophically with one another. It's a testament to a quiet, invisible power, a force that shapes destinies across unimaginable distances. Directly orbiting this magnificent star are 8 planets each, a distinct world with its own unique story. These planets are broadly grouped into 2 families, much like different types of characters in a grand epic. First closest to the Sun are the inner terrestrial planets, Mercury, Venus, Earth, and Mars. Imagine these as the rocky compact core of our system worlds, forged from heavier elements with solid surfaces that speak of ancient impacts and volcanic fire. They are characterized by their relatively modest sizes and dense rocky compositions, intimate worlds where the very ground beneath your feet feels solid and real. Separating these terrestrial worlds from their larger, more distant siblings is the asteroid belt. Picture this as a vast, dusty ring, a cosmic junkyard filled with rocky debris and countless smaller bodies. It's located between the orbits of Mars and Jupiter, a chaotic but surprisingly stable region where remnants from the solar system's chaotic youth continue to orbit, never quite coalescing into a full-fledged planet. These asteroids are like ancient scattered building blocks, remnants of a time when our solar system was still forming whispering tales of cosmic creation. Beyond the asteroid belt lie the majestic outer gas giants, Jupiter, Saturn, Uranus, and Neptune. These are the true behemoths of our solar system, colossal spheres of gas and ice. Imagine them as the gentle giants of our cosmic neighborhood worlds, with no solid surface to stand upon, but instead plunging into layers of swirling hydrogen and helium. Jupiter and Saturn in particular are true to this definition. Immense hydrogen and helium spheres so vast that they dwarf anything in the inner system. Uranus and Neptune, though often grouped with them, have higher concentrations of ice in their interiors and are often affectionately referred to as ice giants. These immense worlds boast significant atmospheres, often swirling with powerful storms and adorned with magnificent ring systems and numerous moons, each a tiny universe unto itself. Further out, still extending beyond Neptune's distant orbit, lies the Kuiper belt. Imagine this as a second, even larger ring of icy bodies, a vast reservoir populated by countless icy relics and dwarf planets like Pluto. It's like a deep freeze archive containing pristine materials, largely unchanged since the very formation of our solar system billions of years ago. The Kuiper belt marks the extended boundary of our solar system's immediate neighborhood, a quiet, cold realm holding clues to its earliest days. And beyond these grand structures filling the space in between and orbiting the planets themselves are countless comets, asteroids, and meteoroids, along with a dazzling array of moons orbiting the planets. These satellites vary widely in appearance and composition, adding to the solar system's incredible diversity, each a unique laboratory for scientific inquiry. Lastly, though still hypothetical in its full extent, the distant Oort cloud is believed to be a vast spherical shell of icy objects, marking the ultimate outer edge of the solar system. Imagine it as a colossal ethereal bubble enveloping our entire cosmic home, serving as the source of long-period comets that occasionally visit the inner solar system, streaking across our skies like ancient messengers from the cosmic deep. This intricate layered architecture of planets, moons, and smaller bodies, all gracefully orbiting the Sun, truly showcases the complex and dynamic nature of our solar system, a system that is both a marvel of cosmic engineering and a cradle of untold wonders. The very definition of a planet has quietly evolved over time, a subtle shift in our cosmic vocabulary as our understanding of the cosmos has expanded. For centuries, our definition was largely based on observation, on what we could see with our eyes or early telescopes. But as our instruments grew sharper and our knowledge deepened, the need for precision became paramount. According to the International Astronomical Union (IAU), the global authority on naming celestial objects, for a celestial body to be classified as a planet within our solar system, it must meet three specific criteria, like three gentle cosmic hurdles. It must clear. Firstly, it must orbit the Sun. This seems straightforward, the fundamental tether to our central star. Secondly, it must be spherical in shape due to its own gravity. Imagine a large enough lump of cosmic material, and its own immense gravitational pull will gently knead it into a sphere, pulling all its rough edges inward. This is a telltale sign of a body with significant mass and internal forces. And thirdly, it must have cleared its orbit of other debris. This is the subtle but profound rule, the one that sparked so much discussion. Imagine a celestial path, a cosmic racetrack. A true planet, by this definition, must be the dominant gravitational force along its orbital path, having swept up or ejected most of the smaller objects in its vicinity. It's like a cosmic bully clearing its own path. This refined definition was formalized in 2006 and marked a quiet turning point for how celestial bodies are classified, particularly affecting one beloved world, Pluto. Discovered in 1930 and long considered the ninth planet of our solar system, Pluto, with its charming heart-shaped region, was affectionately held in the minds of generations as a full-fledged member of our planetary family. However, with this new, more rigorous definition, Pluto was reclassified as a dwarf planet. The reason was simple yet profound. It does not meet the third criterion. Pluto is located in the Kuiper Belt, a vast and crowded region beyond Neptune, teeming with icy bodies and remnants from the solar system's formation. Pluto shares its orbital zone with many other objects, a bustling neighborhood of similar icy worlds. It simply has not cleared its orbit of these other objects, thus gently failing to meet the IAU's strict definition of a planet. This reclassification of Pluto, while stirring considerable debate and even a touch of sadness among the public, was not an act of demotion driven by malice, but rather part of a broader scientific effort to categorize the ever-growing number of discovered bodies in a consistent and meaningful way. It was a recognition that as telescopes and space probes grow more advanced, revealing more about our solar system and beyond the definitions and classifications we use, must continue to evolve, reflecting our expanding understanding of the universe. It was a quiet acknowledgement that our cosmic picture is always becoming clearer, always shifting, always inviting new ways of seeing. Now let's turn our gaze to two fascinating regions of our solar system that hold countless secrets, acting as cosmic time capsules, quietly preserving echoes of our earliest days, the asteroid belt and the Kuiper Belt. Imagine these belts as vast, shimmering necklaces of cosmic jewels scattered across the orbital paths. They are truly treasure troves of information, providing critical insights into the early solar system and the chaotic, yet ultimately creative processes that shaped its formation and evolution. These belts are collections of countless small bodies, often referred to as minor planets, composed of rock metal and ice. They orbit the Sun, much like planets, but crucially, they never quite coalesced into full-fledged worlds. They are the leftover building blocks, the cosmic crumbs from the original celestial feast. The asteroid belt nestled between the orbits of Mars and Jupiter contains remnants from the solar system's tumultuous formation approximately 4.6 billion years ago. Imagine these asteroids as ancient weathered stones, each one a fragment of the primordial cloud from which our sun and planets condensed. By studying these asteroids, scientists can gently glean invaluable information about the materials and conditions that were present in the very early solar system. The sheer diversity of asteroid compositions is a captivating puzzle. From the carbon-rich C types, dark and organic, to the metallic M types gleaming with iron and nickel, and the silicate-rich S types reflecting the stony composition of our inner planets, each type reflects the varied building blocks available during planetary formation. It's like looking at a collection of different colored marbles, each whispering a different tale of creation. The asteroids' orbits and distributions also provide subtle clues about the powerful gravitational influences of nearby planets, particularly Jupiter. Its immense gravity is believed to have acted like a cosmic shepherd, preventing these objects from ever forming a single coherent planet, instead scattering and shaping them into the belt we observe today. Now let's journey further out past the gas giants to the quiet icy expanse of the Kuiper Belt. Extending beyond Neptune's orbit, this realm is home to a wide variety of icy bodies, including the dwarf planets like our beloved Pluto. Imagine this as a deep freeze archive, a vast cold storage facility preserving the pristine conditions of the outer solar system. The composition and distribution of Kuiper Belt objects, KBOs, offer profound insights into the outermost regions of our system. These icy relics are largely unchanged since the solar system's formation, like perfectly preserved ancient artifacts, providing an unparalleled glimpse into its early history. Studying KBOs helps scientists understand the distribution of different types of material in the early solar system and the subtle processes that ultimately led to planet formation. The Kuiper Belt is also thought to be the principal source of short-period comets, those celestial wanderers that visit our inner solar system relatively frequently. When these icy bodies venture close to the Sun and Earth, their ice sublimates, creating magnificent tails of gas and dust, offering researchers a unique opportunity to analyze these ancient primordial substances directly. Imagine them as fleeting messengers carrying samples of the original cosmic dust. Similarly, some asteroids are believed to be the parent bodies of meteorites that have fallen to Earth, offering a direct, tangible means to analyze the early solar system's composition right in our laboratories. In sum, the asteroid and Kuiper belts are not merely remnants of our solar system's formation. They are active fields of study, vibrant archives that continue to reveal secrets about our cosmic neighborhood's past. They are quiet, persistent teachers, aiding our understanding of planetary systems far beyond our own, and whispering tales of how our familiar home came to be. As we drift deeper into the vastness of our solar system, leaving our rocky Earth behind, the atmospheric conditions of other planets offer a fascinating palette of extremities far beyond what we experience on our temperate blue world. Imagine a cosmic art gallery, each planet a different brushstroke of air temperature and pressure. Take Venus, for instance, our closest planetary neighbor. Picture a world cloaked in a thick, suffocating atmosphere composed mainly of carbon dioxide, interwoven with swirling clouds of sulfuric acid. It's a true greenhouse hell, where the atmosphere traps so much heat that surface temperatures soar above 800 degrees Fahrenheit, hot enough to melt lead, and remain perpetually shrouded in a perpetual crushing twilight. The air pressure on its surface is equivalent to being almost a mile deep in Earth's ocean, a truly uninhabitable and hostile environment. It's a stark, fiery contrast to our own breathable air, a warning of what can happen when a greenhouse effect spirals out of control. On the far end of the spectrum lies Mars, the red planet. Imagine a world with an atmosphere so thin, so tenuous, that it offers scant protection. Composed of 95% carbon dioxide, it fails almost entirely to retain heat, subjecting the planet to incredibly frigid conditions that can plummet to minus 195 degrees Fahrenheit at its poles. The air pressure is barely 1% of Earth's at sea level, meaning that liquid water cannot exist stably on its surface, boiling away instantly in the thin air. It's a quiet, cold desert with only whispers of ancient winds stirring its rusty dust. It is a world that whispers of a lost past when water flowed freely, but now stands as a monument to atmospheric loss. Then there are the magnificent gas giants, Jupiter, Saturn, Uranus, and Neptune. Imagine worlds without a solid surface to stand upon, where the atmosphere simply plunges deeper and deeper, eventually transitioning into layers of liquid or metallic hydrogen. On Jupiter, the king of our solar system, the atmosphere is a turbulent, swirling ocean of hydrogen and helium, festering with colossal storm systems larger than Earth itself. The most famous of these is the Great Red Spot, a titanic hurricane that has raged for centuries, a permanent fiery eye on the planet's stormy face. Saturn, though equally grand, has its own unique atmospheric ballet with distinct band patterns caused by powerful jet streams and its magnificent rings, casting long, intricate shadows across its cloudy face. As we venture through these celestial bodies, it becomes clear that the composition and conditions of planetary atmospheres are as diverse as the planets themselves, painting a vivid picture of the climatic extremes that exist within our solar system. Each a unique testament to the myriad ways that worlds can form and evolve far beyond the gentle embrace of Earth's breathable air. They are a constant source of wonder, reminding us of the infinite variations in the cosmic symphony. The moons orbiting the planets in our solar system are far more than mere celestial companions. They serve as crucial keystones in unraveling the vast complexities of the cosmos, significantly enriching our understanding of the universe. Imagine them as a collection of tiny, intricate worlds, each holding its own unique secrets. One of the most captivating examples is Jupiter's moon Europa. Picture a world covered in a smooth, cracked shell of ice, beneath which scientists believe a vast saltwater ocean harbors. This tantalizing possibility of a subsurface ocean, warmed by tidal forces, suggests the tantalizing potential for extraterrestrial life. The ongoing exploration of Europa, with missions planned to probe its icy crust, represents one of humanity's most exciting quests for life beyond Earth. Closer to home, the patient study of our own moon has shed invaluable light on Earth's deep history. Imagine our moon as an ancient cratered diary recording billions of years of impacts and geological processes. By analyzing lunar rocks and studying its formation, scientists have gained profound insights into the early solar system's dynamics and the violent transformative processes that shaped the terrestrial planets, including our own. It's like finding missing pages from our own planetary autobiography. Then there's Saturn's largest moon titan. Picture a world shrouded in a thick, hazy atmosphere, unlike anything else in our solar system. Beneath this orange veil, the Cassini-Huygens mission revealed an astonishingly Earth-like landscape, complete with vast lakes and rivers, not of water, but of liquid methane and ethane. Titan offers a unique glimpse into what Earth-like conditions might look like under drastically different chemical compositions, expanding our very perspective on where life might potentially exist, defying our Earth-centric assumptions. It's a bizarre and beautiful world, a cosmic mirror showing us a distorted yet familiar reflection. Furthermore, moons like Neptune's Triton, which orbits in the opposite direction to its planet's rotation, challenge our long-held understanding of celestial mechanics and formation theories. Such unusual orbits often suggest violent pasts, perhaps a captured dwarf planet rather than one formed in situ. These natural satellites, each with their unique characteristics and profound mysteries, are not merely celestial bodies orbiting larger planets. They are, in essence, windows into the processes that govern planetary systems, offering tantalizing hints at the conditions that may support life and revealing the diverse outcomes of planetary formation and evolution across the vast, silent universe. They are a constant source of new data, new questions and new avenues of exploration, reminding us that even in the familiar there is always more to discover in the dynamic realm of space exploration. Recent years have been marked by a series of truly groundbreaking discoveries that have deepened our understanding of the solar system in profound ways. Imagine these as cosmic postcards arriving from distant worlds, each one revealing a breathtaking new detail about our neighborhood. One of the most significant findings is the compelling evidence of water vapor plumes erupting from the south pole of Saturn's moon Enceladus. Picture geysers of icy particles and vapor shooting hundreds of miles into space from fissures in the moon's surface. This astonishing discovery strongly hints at a vast subsurface ocean beneath Enceladus's icy crust, a warm, salty reservoir that could potentially harbor life. This finding fundamentally challenges the long-held belief that habitable environments are confined solely to planet surfaces. It suggests that life could thrive in unexpected hidden refuges warmed by internal forces far from the sun's direct light. It's like finding a secret living heart within a frozen world. Furthermore, NASA's Parker Solar Probe's daring mission to touch the sun has provided unprecedented insights into our star's turbulent outer atmosphere, or corona. Imagine a spacecraft bravely plunging into the very furnace of our solar system, enduring unimaginable heat and radiation. This audacious mission is unraveling the long-standing mysteries of solar wind acceleration and the complex mechanisms behind the heating of the corona, which is paradoxically hotter than the sun's surface. By flying closer to the sun than any spacecraft before, it is significantly advancing our understanding of solar phenomena, crucial for predicting space weather that can impact Earth. It's like finally being able to reach out and feel the breath of our star. Additionally, the detailed images and data collected by the New Horizons mission during its historic flyby of Pluto in 2015 utterly revolutionized our view of this distant world. Imagine a tiny spacecraft after a journey of nearly a decade, suddenly revealing a vibrant, complex, and dynamic planet where we expected only a static, frozen sphere. New Horizons unveiled a world with towering ice mountains, flowing glaciers of nitrogen ice, and a surprisingly blue atmosphere. This mission transformed Pluto from a mere dot in a telescope into a captivating, geologically active world, with a fascinating story challenging our previous assumptions about the cold outer reaches of our solar system. These discoveries, among countless others, underscore the dynamic nature of our solar system, revealing that it is a place of astonishing variety and complexity, far beyond what was once imagined. Each new mission is like turning a page in a magnificent cosmic book, revealing more profound and beautiful chapters. Now let's consider the very heart of our solar system, the Sun. Its immense power and remarkable stability play a truly foundational role, orchestrating the intricate rhythm and harmony of our entire cosmic neighborhood. Imagine the Sun not just as a giant ball of fire, but as a colossal silent conductor, guiding a magnificent cosmic orchestra. Its immense gravitational pull is the invisible thread that keeps all the planets, comets, and asteroids in their respective orbits. This force maintains a delicate balance, preventing these celestial bodies from either hurtling wildly into the cold, dark void of interstellar space or colliding catastrophically with one another. It's a continuous, invisible embrace that holds our entire system together, ensuring its long-term stability. Moreover, the Sun's radiant energy beamed across millions of miles, as light and heat is the absolute linchpin of life on Earth. Imagine it as a continuous, life-giving flow, nourishing everything from the smallest blade of grass to the most complex ecosystems. It directly drives Earth's intricate climate and weather systems, powering the atmospheric currents, the water cycle, and the very winds that stir our air. It fuels photosynthesis in plants, transforming sunlight into the fundamental energy that forms the base of nearly all food chains, making life on our planet possible. And beyond this direct sustenance, the Sun's rhythms profoundly influence biological rhythms In countless living organisms, from the daily cycles of sleep and wakefulness to the annual patterns of migration and hibernation, beyond Earth, the sun's pervasive impact is evident in the formation of auroras on planets with strong magnetic fields, such as Jupiter and Saturn, where solar particles interact with their magnetospheres to create stunning light displays. It's also visible in the magnificent tails of comets, which always point away from the sun, pushed by the relentless pressure of the solar wind, a cosmic banner unfurling in the solar breeze. Crucially, the sun's stability, characterized by a remarkably consistent output of energy over billions of years, has been a paramount factor in allowing life to flourish on Earth. Imagine a steady, unwavering flame that has burned brightly for eons, providing a conducive and predictable environment for evolution. This enduring stability offered the sustained conditions necessary for complex life to emerge, adapt, and diversify over vast geological timescales. However, this stability, while enduring, is not eternal. The sun is approximately halfway through its life cycle. In about 5 billion years, it will begin its stately transformation, expanding into a red giant, a colossal swollen star that will engulf the inner planets, significantly altering the landscape and fate of our solar system. This central star's profound power and consistent stability have not only shaped the physical arrangement and climate conditions of the solar system, but also meticulously set the stage for the development of life, marking its influence as both nurturing and ultimately transformative, a grand cosmic narrative of creation and change. Finally, let's consider the enigmatic celestial wanderers we call comets, often lovingly described as dirty snowballs of ice dust and rock. Imagine them as pristine cosmic time capsules holding vital clues to the very beginning of our solar system's history and the chaotic, yet ultimately creative processes that shaped its formation. These ancient bodies are believed to be direct remnants from the solar nebula, the colossal cloud of gas and dust from which our sun and all the planets condensed more than 4.5 billion years ago. As such, they carry pristine materials from the early solar system, largely unaltered by the intense heat and gravitational forces that transformed materials on the larger planets. It's like finding perfectly preserved fossils from the very dawn of creation. By studying these icy voyagers, scientists can gently glean profound insights into the original composition of the solar nebula and the intricate dynamics of early solar system formation. This includes understanding the fascinating question of how water and organic materials, the fundamental key ingredients for life, were delivered to the inner planets, including our own Earth. Many theories suggest that comets laden with ice and complex organic molecules may have acted as cosmic delivery trucks, bombarding the early Earth and seeding it with the very building blocks of life. Each time a comet makes its long looping journey and revisits the inner solar system, its ice sublimates directly into gas, bypasses the liquid phase, releasing a magnificent stream of gas and dust that forms the comet's characteristic tail, often stretching for millions of miles across the sky. This spectacular display provides researchers with a truly unique and fleeting opportunity to analyze these ancient primordial substances from a safe distance. Landmark missions, such as the European Space Agency's Rosetta mission, which achieved the unprecedented feat of landing a probe Philae directly onto the surface of Comet 67P Churyumov-Gerasimenko in 2014, have offered unparalleled close-up observations of a comet's nucleus and its precise chemical composition. Imagine a tiny spacecraft bravely touching down on a fast-moving icy mountain, sending back invaluable data. This allowed scientists to shed remarkable light on the early conditions that prevailed in the solar system, offering crucial clues to Earth's own mysterious origins and the profound emergence of life itself. In this way, comets are not merely fleeting celestial wanderers, spectacular though they may be. They are, in fact, key to unraveling the deepest stories of our cosmic neighborhood. Silent witnesses to the universe's grand narrative of creation. They whisper tales of cosmic dust and primordial ice, reminding us of the vast interconnected web of processes that led to the formation of our home and the very possibility of life within it. They are a constant source of wonder, inviting us to peer into the deep past and to consider the profound journey of our own existence as we gently drift further outward, leaving the familiar confines of our solar system behind. Our perspective expands once more, embracing an even vaster and more profound structure, our galactic home, the Milky Way. Imagine a colossal luminous island in the boundless ocean of the cosmos, a place of unimaginable scale and intricate beauty. It is within the majestic embrace of this spiral galaxy that our sun and all its planets reside, a tiny precious speck within an immense cosmic tapestry. The Milky Way, our galactic home, truly sports a complex and majestic structure that has captivated astronomers and dreamers alike for centuries. Imagine it as a grand slow-motion cosmic whirlpool, a colossal pinwheel of stars, gas, and dust, gently turning in the silent vastness of space. At its very heart lies a bulging central region often referred to as the galactic bulge. This dense luminous core is enveloped in a faint ethereal halo, both of which harbor ancient reddish stars. These stars, billions of years old, are like venerable elders, revealing the galaxy's immense maturity and providing profound insights into its earliest days. They are the quiet witnesses to its long unfolding story. Surrounding this core is the galaxy's most defining and iconic feature, its magnificent spiral arms. Imagine these as vast, luminous lanes sweeping gracefully outward from the galactic center. These arms are not merely decorative. They are dynamic arteries of cosmic activity teeming with vast reservoirs of gas and dust and billions of stars. It is within these swirling arms that new stars are born, twinkling into existence from collapsing clouds of gas like countless diamonds being forged in a cosmic furnace. These arms are not only sites of vigorous star formation, but also home to young hot blue-white stars that illuminate the galaxy's swirling patterns, painting a breathtaking picture of dynamic beauty and ceaseless cosmic activity. They are the vibrant, bustling neighborhoods of our galactic city, constantly changing, constantly creating. Encircling the flattened disk of the Milky Way, almost like a ghostly shroud, is a thin spherical halo that stretches far beyond the visible spiral arms. This halo is not empty. It is speckled with globular clusters, tight spherical groupings of hundreds of thousands to millions of stars. Imagine these as ancient glittering celestial jewels, tightly bound by gravity, like magnificent swarms of cosmic bees. These globular clusters are among the oldest inhabitants of the galaxy, bearing silent witness to its early history, offering invaluable clues about its formation and evolution. They are like living fossils, perfectly preserved from a time when our galaxy was young, and embedded within this vast halo, though incredibly difficult to see or directly detect, is the mysterious dark matter that envelops the entire galaxy. Imagine it as an invisible scaffold, a colossal transparent framework that provides the essential gravitational glue, holding the vast structure of the Milky Way together. Without the immense unseen pull of dark matter, our rapidly spinning galaxy would simply fly apart, its stars flung into the cold, desolate emptiness of intergalactic space. It adds an enigmatic beauty to our understanding of the cosmos, reminding us that much of the universe remains veiled in profound mystery. Adding another layer of complexity to its grand design, the Milky Way also features a distinct bar-shaped structure that extends from its core. Imagine a luminous cosmic rod stretching across the galactic heart. This barred shape is a phenomenon common in perhaps 2/3 of all large spiral galaxies observed in the cosmos. Its presence has been a focal point of recent research as astronomers strive to understand its precise role in the galaxy's evolution and dynamics. Does it help funnel gas inward, triggering bursts of star formation? Does it influence the formation and stability of the spiral arms? These are questions that continue to unravel the intricate mechanisms of our galactic home. As we reside within one of its spiral arms, specifically the Orion arm, getting a comprehensive bird's-eye view of the Milky Way's magnificent grand design is inherently challenging, like trying to see your entire city from inside one of its busy streets. Yet through painstaking, ongoing observations from powerful telescopes and sophisticated mapping efforts, astronomers continue to unravel the mysteries of its structure. These dedicated efforts help us to patiently piece together the colossal story of not just our immediate galactic home, but also our place within the universe's vast and ever-expanding tapestry. One gentle whisper of cosmic light at a time, the Milky Way in all its intricate glory is a testament to the elegant chaos and profound beauty of the cosmos. When placed within the vast cosmic tapestry, the Milky Way stands as a testament to the astonishing diversity of galaxy forms and sizes peppered throughout the universe. Imagine a boundless art gallery where each galaxy is a unique masterpiece painted with billions of stars. Our own galaxy is classified as a barred spiral galaxy, a common and elegant design in the cosmos. This structure, characterized by its prominent central bar and sweeping spiral arms, is similar to perhaps 2/3 of all large galaxies observed in the universe, suggesting a shared evolutionary path for many cosmic islands. However, its specific properties and dimensions, when meticulously studied, highlight both its unique characteristics and its commonality within the broader galactic population. In comparison to its more famous spiral siblings, like the magnificent Andromeda galaxy M31, our Milky Way is considered slightly smaller, a close companion rather than an identical twin. Andromeda is a truly colossal spiral, containing about twice the number of stars as our galaxy, a grander, more luminous neighbor. Yet both galaxies, despite their differences in size, are considered average in size and luminosity when compared to the overall galaxy population, which includes true behemoths, like IC 1101, the largest known galaxy stretching over an unimaginable 6 million light-years across. Imagine a cosmic city so vast it dwarfs our entire galactic home, a testament to the extreme scales found in the universe. Our Milky Way, with its approximately 100,000 light-year diameter, pales in comparison to such titans. What truly sets the Milky Way apart, particularly from the more uniform elliptical and irregular galaxies, is its distinctly pronounced spiral structure and its distinct barred region. Imagine the elegant swirling arms pregnant with new star formation, contrasting sharply with the smooth, featureless glow of elliptical galaxies. These features are strong indicators of a dynamic and ongoing history of star formation, stellar evolution, and intricate gravitational interactions. Elliptical galaxies, in contrast, often appear more uniform in shape, like cosmic footballs or eggs, and typically have much less new star formation, populated mostly by older, redder stars. Irregular galaxies, on the other hand, lack a clear, coherent form, appearing chaotic, and often being significantly smaller and less massive. They are like cosmic smudges born from violent interactions or simply never settling into a defined shape. Despite billions of years of evolution, which include complex gravitational interactions with neighboring galaxies and continuous internal changes, the Milky Way steadfastly retains its identifiable spiral structure, a testament to its inherent stability and enduring form. And in a breathtaking display of the universe's dynamic and ever-changing nature, our galaxy is currently on a collision course with the Andromeda galaxy. Imagine two colossal cosmic whirlpools slowly, inexorably drawing closer over immense spans of time. The two are expected to merge in about 4 billion years, a common fate that emphasizes the dynamic and ceaseless evolution of galaxies in the universe. This impending cosmic merger, a slow-motion ballet lasting eons, will significantly alter the structure of both galaxies, forming a new, larger, and perhaps more elliptical galaxy. In this grand cosmic dance, The Milky Way serves as a profound bridge connecting us to the broader cosmic story, illustrating both the incredible diversity and the deep universality of galaxies in crafting the magnificent fabric of the cosmos. It reminds us that nothing in the universe stands still. Everything is in a state of beautiful constant transformation. At the very heart of the Milky Way, shrouded in immense mystery and unimaginable power, lies one of the most enigmatic and compelling objects in the cosmos, a supermassive black hole known by the unassuming name of Sagittarius A. Imagine it as the quiet gravitational king of our galaxy, an invisible behemoth whose influence extends far beyond its immediate vicinity. This colossal black hole possesses a mass equivalent to about 4 million times that of our Sun. Picture 4 million suns squeezed into a space smaller than Mercury's orbit. The sheer density and gravitational pull are almost beyond human comprehension. This immense gravitational force orchestrates the precise, rapid orbits of stars and gas clouds that reside in the galaxy's central region, forcing them into dizzying cosmic dances around an unseen center. Despite its staggering mass, SGRAE is remarkably quiet compared to the incredibly active galactic nuclei found at the centers of many other galaxies. It's like a sleeping giant, only occasionally stirring from its slumber. Only rarely does it flare up briefly, emitting immense amounts of radiation as it interacts with surrounding matter that happens to stray too close and is pulled into its powerful gravitational embrace. The very presence of SGRAE was initially inferred from the incredibly precise movements of stars near the galaxy's core. Their rapid, almost frantic orbits, far faster than could be accounted for by visible matter alone, were clear indicators of the overwhelming influence of a massive, compact, unseen object. This inference was further bolstered and confirmed by subsequent radio and X-ray observations, which revealed emissions characteristic of matter being heated and stressed near a black hole's event horizon. All the evidence points to this supermassive black hole as the true central pivot around which the entire Milky Way quietly turns a cosmic anchor for billions of stars. The environment in the immediate vicinity of SGRAE is a crucible of extreme conditions and a true hotbed of astronomical phenomena. Imagine a realm where the laws of physics are pushed to their very limits. Intense tidal forces, which can stretch and tear apart anything that ventures too close, are a constant presence. Relativistic effects, where time and space warp and bend in profound ways due to the extreme gravity, are not abstract theories here, but daily realities for the orbiting stars and gas. This provides a natural, unparalleled laboratory for studying the fundamental physics of black holes and their profound impact on galaxy formation and evolution. How does such a colossal object influence the birth and death of stars around it? How does it help sculpt the shape and destiny of the entire galaxy? These are some of the deepest questions scientists are asking. The supermassive black hole at the center of the Milky Way is not just a focal point of the galaxy's immense structure, but also an object of intense scientific inquiry. Researchers are constantly seeking to unravel the profound mysteries of its origins, its subtle behavior, and the precise roles such cosmic giants play in the grand cosmic ballet of the universe. It reminds us that even at the heart of our familiar galaxy, there are still unfathomable depths and silent forces at play waiting to be understood, inviting us to ponder the very fabric of reality itself. It is a quiet, powerful presence that continues to challenge and expand our understanding of the universe. Now let us turn our gaze from the grand structures of galaxies to the very building blocks that illuminate them, the stars. Imagine each star as a cosmic individual, born from dust, living a fiery life and eventually fading, often in spectacular fashion. Stars begin their luminous lives in the cold, dense cores of molecular clouds. Picture these as vast, dark, dusty nurseries, colossal reservoirs of gas and dust scattered throughout galaxies. Within these quiescent clouds, regions of slightly higher density, often catalyzed by cosmic events like the powerful shock waves from nearby supernova explosions, begin a slow, inexorable collapse under their own immense gravity. This is the quiet, patient initiation of the process of star formation. As the collapsing region, now a nascent protostar, continues to pull in more and more material from its surroundings, its core heats up under the increasing pressure. This continues for millions of years, a slow simmering, until the temperature and pressure in its heart reach unimaginably high levels, high enough to ignite nuclear fusion. This ignition is the moment a star is truly born. At this point, the immense gravitational pull which seeks to collapse the star further is perfectly counteracted by the outward pressure generated by the tremendous outflow of energy from the fusion of hydrogen into helium in the star's core. This marks the glorious birth of a new star, a self-sustaining cosmic furnace that will shine for millions or even billions of years. It enters its long, stable main sequence phase, like our own sun peacefully converting hydrogen into helium. The life cycle of a star is primarily determined by one crucial factor: its mass. Imagine two candles, one tiny and one massive. The tiny one will burn slowly for a very long time, while the massive one will blaze fiercely and burn out quickly. Smaller stars like our sun are like the patient, long-burning candles. They spend billions of years steady and consistent, fusing hydrogen in their cores, gently illuminating their planetary systems. Once the hydrogen fuel in their core is exhausted, a profound transformation begins. They expand dramatically and cool, entering a red giant phase, becoming colossal luminous spheres. During this phase, they begin to fuse helium into heavier elements like carbon and oxygen in their core. Eventually, their outer layers are gently ejected into space, forming beautiful, expanding shells of gas known as planetary nebulae. What remains behind is a dense, incredibly compact core called a white dwarf, a stellar remnant roughly the size of Earth, but with the mass of the Sun. This white dwarf slowly cools over unimaginable spans of time, eventually fading into a cold, dark cinder. More massive stars, however, lead much shorter, far more tumultuous and dramatic lives. Imagine them as dazzling fireworks, burning through their nuclear fuel at a furious rate. They are truly cosmic gourmands, consuming their hydrogen far more quickly. Their immense gravity allows them to fuse heavier and heavier elements in their cores, progressing rapidly through the stellar fusion chain, from helium to carbon, then oxygen, neon, magnesium, silicon, and eventually to iron. This is the crucial turning point, the beginning of the end. Iron is a unique element because its fusion does not generate energy. In fact, it consumes energy. This lack of energy generation leads to a catastrophic instability in the star's core. Without the outward pressure from fusion to counteract gravity, the iron core collapses almost instantaneously under its own immense weight. This sudden collapse triggers a colossal, unimaginably powerful explosion known as a supernova, an event so bright that it can briefly outshine entire galaxies, a final, glorious cosmic roar. What remains after this cataclysm depends entirely on the star's initial mass. For less massive stars, the core collapses into an incredibly dense object called a neutron star, a sphere only a few miles wide, but packing more mass than the Sun, so dense that a spoonful would weigh billions of tons. For the most massive stars, the collapse is even more extreme, leading to the formation of a black hole, an object whose gravity is so overwhelmingly strong that not even light can escape its grasp. This continuous cycle of star birth and death is a truly fundamental process in the universe, an eternal cosmic recycling program. The remnants of dead stars, the heavy elements forged in their fiery cores, or during their violent supernova explosions, are ejected into the vastness of space. These elements, carbon, oxygen, iron, gold, silver, uranium, are the very ingredients necessary for the formation of future stars, for the planets that orbit them, and ultimately for life itself. Each stellar end marks the gentle beginning of a new chapter in the cosmic saga, with the scattered remnants of one generation of stars contributing to the birth of future generations woven intricately into the very fabric of the universe. It's a beautiful ongoing dance of creation and destruction, a testament to the universe's ceaseless journey of becoming. As we continue our gentle journey through the cosmos, having marveled at the grand structures of galaxies and whispered about the birth and death of their stellar inhabitants, let us now pause to appreciate the sheer diversity within the realm of stars themselves. Imagine gazing into a vast cosmic garden, where each flower, though fundamentally similar in its essence, displays a dazzling array of types, each distinguished by unique characteristics, such as its mass temperature, luminosity, and ultimately its lifespan. Just as the color and size of a flower hint at its internal processes, so too do the observable properties of stars reveal the intricate physics at play within their fiery hearts. A pivotal tool in astrophysics, a kind of cosmic map or family tree for stars, is the Hertzsprung-Russell HR diagram. Imagine this as a magical chart that plots stars based on their luminosity, how bright they intrinsically are against their temperature, often reflected in their color. By placing countless stars on this diagram, astronomers have revealed a broad spectrum from the cool, dim, shy stars to the hot, luminous, blazing giants. This diagram is not just a classification tool. It's a narrative showing us the life stages of stars and how they evolve over billions of years. At one end of this stellar spectrum, we find the humble yet incredibly numerous red dwarfs. Imagine them as tiny flickering embers, small cool stars with very low mass and a distinct reddish hue. They are the most common type of star in the Milky Way, truly the quiet majority. What sets them apart is their incredible longevity. Due to their remarkably efficient fusion of hydrogen, they burn through their nuclear fuel at an incredibly slow pace, capable of glowing for trillions of years. While our sun has a lifespan of about 10 billion years, a red dwarf might shine for hundreds of billions or even a trillion years, outliving the current age of the universe many times over. They are the enduring, patient, and quiet inhabitants of our galaxy, perhaps providing stable homes for planets for unimaginably long periods. Their small size means they don't generate the intense pressures and temperatures of larger stars, allowing them to conserve their fuel and continue their slow, steady burn across cosmic eons. They are the unassuming marathon runners of the universe, destined to shine long after all other stars have faded. Moving up in temperature and luminosity on our cosmic chart, we encounter the vast family of main sequence stars. Our own sun belongs to this category, a comfortable, middle-aged member of this vibrant group. These stars are in their most stable phase of life, diligently fusing hydrogen into helium in their cores, maintaining a delicate balance between the inward pull of gravity and the outward push of fusion energy. Imagine them as the reliable, steady engines of the cosmos, consistently churning out light and heat. These main sequence stars vary widely in color, ranging from deep red to brilliant blue-white, a direct reflection of their surface temperatures. The sun, with its warm, familiar glow, is classified as a yellow dwarf, a medium-sized star that has been the consistent anchor for life on Earth for billions of years. They are the backbone of most galaxies, providing the steady light that makes complex planetary systems possible. Their internal structure is like a well-oiled machine, carefully balancing immense forces to maintain a stable output of energy. Beyond the main sequence, the HR diagram shows us the later, more dramatic stages of stellar evolution. Here we find the magnificent giant and supergiant stars. Imagine stars that have swollen to colossal proportions, their outer layers expanding as their cores undergo new phases of fusion. Giants are significantly larger and more luminous than their main sequence counterparts, but paradoxically, they are cooler, which gives them a distinct red or orange appearance. Our own sun will one day become a red giant, expanding to engulf the inner planets, a poignant reminder of the transient nature of even our most stable cosmic companion. They are stars that have used up most of the hydrogen in their cores and are beginning to fuse helium, causing their outer layers to puff out. Supergiants are in a league of their own. They are among the most massive and luminous stars in the entire universe, true celestial titans. Imagine stars so bright that they can outshine entire galaxies, their brilliance almost overwhelming. However, their sheer size and luminosity come at a cost. They lead incredibly short, furious lives, burning through their nuclear fuel at an astonishing rate. Their brief, dazzling existence often ends dramatically in spectacular supernova explosions, a cataclysmic final act that scatters their heavy elements across the cosmos. They are the cosmic fireworks, burning bright and fading fast, but leaving an immense legacy behind. Their internal pressures are so extreme that they fuse elements all the way up to iron, leading to their ultimate explosive demise. On the extreme end of temperature, we have the dazzling blue dwarfs and blue giants. Imagine stars burning with an intense, almost ethereal blue light, boasting some of the hottest surfaces in the universe. This extreme temperature is what gives them their distinct blue coloration. These stars are much rarer than red dwarfs or yellow main sequence stars, and like the supergiants, they live fast and die young, burning through their nuclear fuel at a remarkable rate. They are truly cosmic sprinters, blazing fiercely for a relatively brief cosmic moment before moving on to their next evolutionary stage. Their intense heat and radiation profoundly influence their surrounding interstellar medium, often triggering new star formation in nearby gas clouds. Finally, another crucial class of celestial objects includes the remnants of stars that have completed their nuclear burning phases. Silent echoes of once vibrant suns. These are the fascinating products of stellar death, leaving behind incredibly dense and compact objects. First, we have white dwarfs. Imagine a tiny, incredibly dense diamond, the compact remains of medium-mass stars like our Sun. After shedding their outer layers, these objects are left with a core roughly the size of Earth, but packing the mass of the Sun. They are incredibly dense. A spoonful of white dwarf material would weigh tons. Yet, they are no longer massive enough to continue nuclear fusion in their core. They slowly cool over billions of years, radiating away their residual heat, eventually fading into hypothetical black dwarfs. Cold, dark, and invisible cosmic embers. They represent the quiet, dignified end for the majority of stars in our universe. Next, born from the most violent stellar deaths, are neutron stars. Imagine the entire mass of a star larger than our Sun, crushed down into a sphere only about 10 to 20 kilometers wide, roughly the size of a city. These are the superdense remnants of supernova explosions so incredibly compressed that their matter consists almost entirely of neutrons. Their density is truly staggering. A single teaspoon of neutron star material would weigh billions of tons, equivalent to all the cars on Earth. They are incredibly powerful, often spinning rapidly and emitting beams of radiation, acting as cosmic lighthouses known as pulsars. They are the universe's ultimate cosmic crushing machines, a testament to the extreme forces unleashed in a supernova. Their magnetic fields are also incredibly strong, billions of times more powerful than Earth's, further contributing to their fascinating properties. Lastly, and perhaps most enigmatic of all, are black holes. Imagine a cosmic abyss formed from the collapse of the most massive stars. These objects possess gravity so overwhelmingly strong that not even light, the fastest thing in the universe, can escape their grasp once it crosses a boundary called the event horizon. They are the ultimate cosmic prisons, invisible to direct observation, but their presence is profoundly felt by their gravitational influence on nearby stars and gas. They are the universe's ultimate mystery, pushing the boundaries of our understanding of space-time and gravity. Their immense density warps space-time around them, creating a gravitational well from which nothing can return. They represent the most extreme endpoints of stellar evolution. Silent devourers of light and matter. Each type of star, from the smallest red dwarf to the most colossal supergiant, plays a truly pivotal role in the cosmos. Some, like our Sun, nurture planets with stable warmth, providing the consistent conditions necessary for life to emerge and evolve. Others, through their spectacular violent demises in supernova explosions, seed the universe with the heavy elements, the carbon, oxygen, iron, and gold, that are necessary for the formation of new stars, new planets, and ultimately, new life. Imagine every atom in your body, save for hydrogen, having been forged in the heart of a star or in the crucible of a supernova. Their immense variety, their diverse life cycles, and their ultimate fates are central to the unfolding story of the universe's grand evolution, an eternal cosmic ballet of creation and destruction, endlessly enriching the cosmos with the building blocks of existence. They remind us of the deep connection between the smallest particles and the grandest cosmic events, a unity that whispers through the silent reaches of space. Now, as we contemplate these immense, dazzling celestial objects, a fundamental question emerges. How do we possibly measure the vast distances to these distant suns? Given that our instruments remain tethered to our own tiny world, measuring distances in the vast expanse of our galaxy, the Milky Way is a complex and ingenious endeavor, a testament to human ingenuity and cosmic curiosity. Astronomers tackle this challenge using a variety of ingenious methods, each suited to different scales within the galactic tapestry, like a cosmic distance ladder where each rung allows us to reach a bit further. One fundamental and wonderfully elegant technique, particularly for relatively nearby stars within our Milky Way, is the use of parallax. Imagine holding your finger out in front of you and closing one eye, then the other. Your finger appears to shift against the distant background. Parallax relies on this very principle. As Earth makes its annual journey around the Sun, a vast orbit of 186 million miles, the apparent position of a nearby star subtly shifts against the backdrop of more distant, seemingly fixed stars. By precisely measuring this tiny apparent shift, this cosmic wobble, astronomers can, with the elegant simplicity of trigonometry, calculate the distance to stars up to a few thousand light-years away. It's a method as old as geometry itself, but now executed with incredible precision, acting as the foundational rung of our cosmic ladder. This method is most accurate for stars that are relatively close to us, as the parallax angle becomes infinitesimally small for distant objects, making it incredibly difficult to measure. For objects far beyond the immediate reach of parallax, where the cosmic wobble becomes too faint to measure accurately, astronomers turn to the concept of standard candles. Imagine finding objects in the universe whose intrinsic brightness, their true inherent luminosity, is known. If you know how bright a light bulb truly is, you can determine how far away it is simply by observing how bright it appears to be. One of the most reliable and powerful standard candles in the cosmos is a specific type of exploding star known as a type Ia supernova. Imagine a star reaching a critical mass, triggering a sudden cataclysmic explosion that briefly outshines entire galaxies. These magnificent events occur when a white dwarf star, the dense remnant of a medium-mass star, accretes enough material from a companion star to undergo a runaway nuclear fusion reaction. Crucially, these explosions are believed to always reach roughly the same peak luminosity, meaning they are incredibly consistent in their true brightness. Since type Ia supernovae have a remarkably consistent known luminosity, astronomers can calculate their immense distance simply by comparing their apparent brightness as seen from Earth. They are like cosmic light bulbs shining with a consistent wattage visible across unimaginable cosmological distances. Another pivotal and fascinating tool in our cosmic distance ladder is the observation of Cepheid variable stars. Imagine stars that breathe rhythmically, expanding and contracting, causing their luminosity to pulsate in a highly predictable pattern. The brilliance of Cepheid variables lies in a fundamental relationship discovered by Henrietta Leavitt in the early 20th century the period of their pulsations, how long it takes them to brighten and dim, is directly and precisely related to their intrinsic brightness. Imagine a cosmic clock that tells you not just the time, but also the wattage of the light bulb it's attached to. By measuring the pulsation period of a Cepheid variable, astronomers can determine its true luminosity. Then by comparing this true luminosity with the star's apparent brightness as observed from Earth, they can accurately determine its distance. Cepheids have been instrumental in measuring distances within our Milky Way and to nearby galaxies, acting as reliable milestones in the vast cosmic landscape. Additionally, astronomers employ other clever techniques that extend our reach even further into the extragalactic scales. These include empirical relationships, like the Tully-Fisher relation, which beautifully links the luminosity of spiral galaxies to their rotation speed. A faster spinning galaxy tends to be more massive and therefore more luminous. Similarly, the Faber-Jackson relation applies to elliptical galaxies, based on a correlation between their luminosity and the dispersion of stellar velocities within them. These methods, alongside ever-evolving technologies and the increasing precision of data from ground-based telescopes and future space observatories, continually refine and expand our understanding of the Milky Way's intricate structure and our tiny place within the boundless cosmos. They are like ever-lengthening measuring tapes, allowing us to map the universe with increasing detail, gently paving the way for profound insights into the universe's most enduring mysteries. Each rung on this cosmic ladder builds upon the last, allowing us to piece together the immense tapestry of our universe in a comprehensible manner, offering whispers of its age, its expansion, and the magnificent distribution of galaxies within the cosmic web. Now let us gently expand our gaze once more, moving beyond the individual stars and even our own magnificent Milky Way to contemplate the truly immense, large-scale structure of the universe itself. Imagine an intricate, almost impossibly vast celestial tapestry, woven not from threads, but from galaxies' gas and the mysterious dark matter. This immense structure, far from being a chaotic jumble, reveals itself as a complex hierarchical and beautifully organized web-like pattern, often referred to as the cosmic web. It's like a colossal glowing sponge or a celestial spider web, stretching across the vast emptiness of space, outlining the very architecture of reality. This colossal structure is composed of long luminous filaments of galaxies and intergalactic gas that stretch for hundreds of millions of light years. Imagine them as shining threads, cosmic highways of matter connecting the densest concentrations of galaxies at their intersections. These filaments are not just random alignments. They are the backbone of the universe, outlining the paths along which galaxies have flowed and clustered over billions of years. Interspersed within this grand network are vast, desolate voids of empty space. These appear as immense dark bubbles regions with relatively few galaxies seeming almost entirely devoid of matter. These voids can be hundreds of millions of light years across, a testament to the universe's incredible emptiness and sparsity in certain regions. The cosmic web in its intricate glory is the largest scale structure in the universe that we can observe. Its very existence is a direct consequence of the subtle initial irregularities in the distribution of matter in the incredibly early universe, just moments after the Big Bang. Over billions of years, these tiny fluctuations in density were magnified by the relentless, pervasive gravitational pull of dark matter. Dark matter, which we will whisper about more deeply, later acts like an invisible scaffold, creating the underlying gravitational potential that guides the formation and clustering of galaxies and galaxy clusters within this vast cosmic framework. Without this unseen gravitational influence, the delicate strands of the cosmic web simply would not have formed. At the smallest observable scale of this grand hierarchy, we find galaxy groups. Imagine these as small, intimate gatherings consisting of a few to dozens of galaxies, all gravitationally bound together in a quiet, celestial dance. Our own Milky Way is a cherished member of such a group known as the local group. This includes our magnificent spiral neighbor, the Andromeda Galaxy, and about 50 other smaller dwarf galaxies, all quietly interacting and orbiting their collective center of mass. These groups are the fundamental building blocks, the foundational nodes from which much larger structures emerge like tiny pearls on a necklace. These galaxy groups are themselves the components of even grander structures, known as galaxy clusters. Imagine these as bustling cosmic cities, colossal gatherings that can contain hundreds to thousands of galaxies, all stretched over millions of light years. The Virgo cluster, the closest large galaxy cluster to our Milky Way, is a prime example of such a cosmic metropolis housing over 1,000 galaxies, all subtly influencing each other with their gravitational embrace. Clusters and groups in turn are themselves linked by the previously mentioned filaments, massive elongated structures of galaxies, and dark matter that form the luminous boundaries between the vast voids. These intricate filaments and voids, in their totality, resemble a complex interconnected sponge, or more poetically, a vast cosmic web stretching across the observable universe. The next level up in this astonishing hierarchy are the superclusters. Imagine these as the ultimate cosmic metropolises, where galaxy clusters and groups connected by filaments form even larger, more immense concentrations of matter. Our own Milky Way, as part of the local group, is itself part of the Laniakea supercluster. This truly immense structure contains tens of thousands of galaxies, spread over an area of 500 million light-years, all slowly drifting towards a common gravitational center. The very name, Laniakea, means immense heaven in Hawaiian, a fitting tribute to its staggering scale. The very distribution and clustering of galaxies on such massive scales are largely influenced by those initial tiny fluctuations in density that existed in the universe shortly after the Big Bang. These minute variations, magnified by the relentless gravitational pull of dark matter, have sculpted the complex filamentary structure of the cosmos that we observe today. Imagine dark matter as the invisible scaffolding creating the underlying gravitational framework, with galaxies subsequently forming and evolving within this dark unseen architecture over billions of years. The mutual gravitational attraction between galaxies, along with the mysterious influence of dark energy, which is paradoxically accelerating the expansion of the universe, has sculpted this intricate cosmic web. This grand cosmic structure reveals so much about the fundamental properties of the universe and the immense forces that have shaped it throughout its history. It is a constant reminder of the universe's hidden order, its subtle elegance, and the profound questions that still beckon us. Now, let us turn our attention to the profound and sometimes terrifying role of black holes. Those enigmatic objects with gravitational fields so overwhelmingly intense that not even light, the swiftest thing in the universe, can escape their grasp. Imagine them as silent, insatiable cosmic abysses. They play a truly pivotal role in the dynamics and evolution of galaxies, quietly shaping their destinies over billions of years. At the very heart of nearly every large galaxy, including our own Milky Way, resides a supermassive black hole. Imagine this as the galaxy's gravitational anchor, a silent, powerful conductor that can influence the galaxy's structure and behavior in profound ways, orchestrating the dizzying dance of billions of stars. One of the key roles of these supermassive black holes is in galactic nuclei activity. When immense amounts of matter, whether gas clouds or unlucky stars, spiral inward towards a black hole, they form a rapidly rotating accretion disk around it. The incredible gravitational forces and friction within this disk heat the infalling material to millions of degrees, causing it to radiate intensely across the entire electromagnetic spectrum, from radio waves to gamma rays, before finally crossing the point of no return, the event horizon. This process can fuel the incredibly luminous cores of active galaxies, known as quasars, which we will revisit shortly, and active galactic nuclei AGN, making some of them visible across vast cosmic distances. They are like cosmic beacons shining brightly from the distant past. The immense energy released from these active black holes can have a dual profound effect on star formation in the surrounding galaxy. On one hand, it can trigger bursts of star formation by compressing nearby gas clouds through powerful shock waves acting as a cosmic catalyst. On the other hand, these energetic outflows can also sweep up and clear out vast amounts of gas within a galaxy, potentially inhibiting further star formation by removing the very raw material needed for new stars. This intricate feedback mechanism helps regulate the pace of star formation in galaxies and contributes significantly to their structural development over vast cosmic time. It's a delicate balancing act, a push and pull, that sculpts the very fabric of galactic evolution. Moreover, the overwhelming gravitational influence of supermassive black holes profoundly affects the orbits of stars near the galactic center. Imagine stars whipped into dizzying speeds, their paths profoundly altered by the unseen gravitational behemoth. This leads to incredibly high stellar velocities and creates dense stellar environments where stars are packed much more closely together than in the outer regions of the galaxy. This dynamic interaction can also contribute to the growth of the black hole itself as it continues to accrete matter and to the evolution of the galactic core, including shaping the bulge, the dense group of stars surrounding the galactic center. In the grand scheme of galaxy mergers and interactions, black holes can play an even more crucial role in the final dramatic stages of the merging process, as two galaxies slowly collide and eventually combine their central supermassive black holes. Once separate entities begin a long spiraling dance towards each other, they form a binary black hole system slowly drawing closer, radiating energy in the form of gravitational waves. Eventually, these two colossal black holes merge into an even more massive black hole, a truly cataclysmic event. This merger can send incredibly powerful gravitational waves, ripples in the very fabric of spacetime, reverberating across the cosmos, a phenomenon famously predicted by Albert Einstein's theory of general relativity over a century ago, and directly detected for the first time by the LIGO and Virgo observatories in recent years. This new window into the universe allows us to hear the universe's most violent events. Thus, black holes are far from mere cosmic oddities or theoretical curiosities. They are, in fact, instrumental in shaping the galaxies they inhabit. Their profound influence extends from the very heart of galaxies to their broader structure and evolution, marking them as key players in the majestic slow-motion cosmic ballet of the universe. They are a constant reminder of the extreme power and elegant chaos that govern the largest scales of reality, inviting us to ponder the deepest mysteries of gravity and space-time. Now, let us turn our attention to one of the universe's most enigmatic and powerful phenomena: quasars, or quasi-stellar objects. Imagine them as brilliant ancient lighthouses blazing from the very edges of the observable universe, illuminating the cosmos with an intensity almost beyond comprehension. They are quite simply among the most luminous, powerful, and energetic phenomena in the entire universe, emitting light and other forms of radiation across the entire electromagnetic spectrum, from the longest radio waves to the most energetic gamma rays. Quasars are found at the centers of some galaxies, particularly those in the young distant universe. Their incredible power is not fueled by nuclear fusion like stars, but by supermassive black holes accreting matter at an exceptionally high rate. Picture a colossal black hole, millions or even billions of times the mass of our Sun, greedily pulling in vast amounts of gas and dust from its surrounding galaxy. As this matter spirals inward towards the black hole, it forms an incredibly hot, rapidly rotating accretion disk around it. The immense gravitational forces and friction within this disk heat the infalling material to unimaginably extreme temperatures, millions of degrees Celsius, causing it to radiate intensely. This blazing accretion disk is what we observe as a quasar, a beacon of light, powered by the gravitational appetite of a central black hole. Quasars are absolutely crucial for understanding the early universe. Because they are so incredibly luminous, they can be seen over vast cosmic distances, stretching across billions of light years. This means that when we observe a quasar, we are literally looking back in time, seeing it as it was billions of years ago when the universe was much younger and very different from today. They provide us with a unique, unparalleled glimpse into the past, allowing astronomers to study the conditions and processes at play during the infancy of the universe. Imagine them as ancient photographs capturing moments from a time long, long ago. Their light can also serve as a profound probe for the intervening space between the quasar and US, revealing invaluable information about the distribution of matter, including distant galaxies and vast, diffuse intergalactic gas clouds through which the quasar's light has traveled for eons. It's like shining a powerful flashlight through a misty landscape, revealing the hidden structures within. Moreover, the meticulous study of quasars contributes significantly to our understanding of galaxy evolution and the crucial role of supermassive black holes in shaping their host galaxies. The profound correlation between the masses of these central black holes and the properties of their host galaxies suggests a deep, intricate link between the growth of the black holes and the evolution of the galaxies themselves. This relationship indicates that quasars and the supermassive black holes that power them have played a truly significant and active role in shaping galaxies throughout cosmic time, influencing their star formation rates, their overall structure, and their eventual destinies. They are not just passive observers, but active participants in the cosmic dance. Quasars also present an extraordinary opportunity to challenge our understanding of physics under extreme conditions. The energetic processes that occur in the immediate vicinity of the event horizon of these supermassive black holes offer unique natural laboratories for studying the fundamental laws of physics in regimes that are utterly impossible to replicate on Earth. They are places where space-time is profoundly warped, where matter behaves in exotic ways, and where our theories are truly put to the test. Thus, quasars illuminate some of the most profound questions about the structure, evolution, and ultimate fate of the universe, providing invaluable insights into the processes that govern the formation and growth of supermassive black holes, the intricate evolution of galaxies, and the large-scale distribution and state of the cosmic web that forms the very backbone of the universe. They are a constant source of awe and a reminder of the universe's boundless energetic mysteries. As we continue our profound journey through the quiet cosmic night, having explored the grand architecture of galaxies and the fiery lives of stars, let us now turn our minds to the most sweeping and fundamental questions of all, the very origin and ultimate fate of the universe. Imagine standing at the edge of an infinite ocean, gazing at a horizon that stretches beyond time itself. Cosmology, the study of the universe as a whole, gently invites us to ponder these vast, almost unfathomable concepts. The prevailing cosmological model that attempts to describe the origin and evolution of the universe is known as the Big Bang Theory. Imagine it not as a conventional explosion in space, but rather as the rapid, spectacular expansion of space itself, carrying all matter and energy outward from an unimaginably hot and dense initial state. According to this theory, the universe began approximately 13.8 billion years ago from this singular point and has been expanding and cooling ever since. It's a continuous cosmic breath, inhaling and exhaling, stretching the very fabric of reality. In the very first fleeting moments following the Big Bang, the universe was an unimaginably hot and dense soup of energy and fundamental particles. Conditions were so extreme, so beyond our earthly comprehension, that particles and their antimatter counterparts were constantly being created and annihilated in a furious dance. As the universe began its rapid expansion, the temperature and density began to rapidly decrease, allowing for the formation of the most fundamental particles we know, quarks and electrons. Within the first few minutes, as the universe continued to cool, these quarks combined to form the first building blocks of atomic nuclei, protons and neutrons. This incredibly brief but profoundly important period of rapid element formation is known as nucleosynthesis, where the lightest elements were forged in the universe's primordial furnace. However, it would take a bit longer, some hundreds of thousands of years, for the universe to cool sufficiently to allow electrons to be captured by these newly formed nuclei. This crucial event, known as recombination, marked a truly transformative period. Prior to recombination, the universe was an opaque, swirling fog of charged particles where light could not travel freely, constantly scattering off the free electrons. But once the electrons were captured, forming the first neutral atoms, primarily hydrogen and helium, the universe suddenly became transparent to light for the very first time. This momentous event led to the release of the cosmic microwave background radiation, CMBR, a faint ancient glow that permeates the entire universe. Imagine it as the universe's baby picture, a direct echo from a time when light first broke free, offering us a snapshot of the infant cosmos. The Big Bang Theory is not merely a grand tale. It is strongly supported by multiple pieces of compelling observational evidence, like different puzzle pieces fitting together perfectly to reveal the whole picture. One of the strongest and most profound pieces of evidence is the aforementioned CMBR. It was accidentally discovered in 1965 by Arno Penzias and Robert Wilson, two engineers who were puzzling over a persistent unexplained static in their radio antenna. This discovery, a uniform low-energy radiation field that can be detected in all directions in space, perfectly matched the Big Bang's predictions, earning them the Nobel Prize in Physics. It's like finding the faint, warm afterglow of a distant ancient fire. The theory is also powerfully supported by the observed redshift of distant galaxies. Imagine stretching a rubber band with dots on it. As the band stretches, the dots move further apart, and if you imagine light waves traveling across it, their wavelengths would also be stretched, shifting towards the red end of the spectrum. This redshift indicates that distant galaxies are consistently moving away from us, and the farther away they are, the faster they recede. This universal recession is the very hallmark of an expanding universe, precisely as predicted by the Big Bang. Furthermore, the theory is beautifully consistent with the relative proportions of light elements, such as hydrogen, helium, and lithium, observed throughout the universe. These abundances align remarkably well with predictions from nucleosynthesis, the early cosmic forging, providing yet another powerful confirmation. Over the decades, the Big Bang Theory has been refined and strengthened with additional observations, and remains the best explanation for the origins and large-scale structure of our universe. However, it continues to be developed and elaborated upon as new astronomical observations are made, constantly contributing to our ever-deepening understanding of the cosmos, one gentle whisper of cosmic truth at a time. Since that initial cosmic ignition approximately 13.8 billion years ago, the universe has undergone a truly remarkable and intricate evolution, transforming from an incredibly hot, dense point into the vast, complex cosmos we observe today. Imagine it as a grand slow-motion ballet where every movement leads to the next, shaping the very fabric of existence. In the immediate aftermath of the Big Bang, the universe was in a state of extreme heat and density, so intense that conditions were beyond our wildest earthly comprehension. It was a primordial soup where particles and antiparticles were constantly being created and annihilated in a furious, energetic dance. As the universe began its rapid and continuous expansion, it gradually cooled sufficiently for the first stable particles to form quarks and electrons. Within the first few minutes, as this cooling continued, these quarks combined to give rise to the familiar protons and neutrons, the fundamental building blocks of atomic nuclei. This brief but profoundly important period, where the very first light atomic nuclei were forged, is known as nucleosynthesis. However, it would take a bit longer, some hundreds of thousands of years, for the universe to cool further. During this crucial era, the temperature finally dropped enough to permit electrons to be captured by these nuclei, thus forming the first neutral atoms, primarily hydrogen and helium. This pivotal moment, known as recombination, was truly transformative. Prior to recombination, the universe was an opaque, swirling fog of charged particles where light could not travel freely, constantly scattering off the unbound electrons. But once neutral atoms formed, the universe suddenly became transparent to light for the very first time. This momentous event allowed light to stream freely through space, leaving us with the cosmic microwave background radiation, CMBR, a faint ancient glow that permeates the entire universe, providing us with a direct snapshot of the infant universe that astronomers can still observe today. It is the universe's quiet echo, a gentle hum from the dawn of time. Following recombination, the universe entered a period often referred to as the cosmic dark ages. Imagine a vast, silent expanse populated primarily by diffuse hydrogen and helium gas, but with very little light. There were no stars, no galaxies, only the fading afterglow of the Big Bang. It was a time of quiet anticipation, a cosmic twilight before the first cosmic dawns. Eventually, however, the relentless, pervasive force of gravitational attraction began its subtle work. Regions of slightly denser matter, those tiny initial irregularities, began to slowly collapse under their own immense weight, like invisible cosmic whirlpools. This slow gravitational accretion led to the formation of the first stars and galaxies illuminating the cosmos for the very first time. The light from these first generations of stars, colossal and short-lived, was powerful enough to end the cosmic dark ages. Their intense energy ionized the surrounding gas, transforming it and allowing it to be seen again, a transition known as rionization. This marked the true dawn of the universe, as we know it, filling the once dark expanse with the radiant glow of countless celestial objects. Over billions of years, stars and galaxies continued to form, evolve, and in many cases merge, creating even larger and more complex structures. These larger structures, such as galaxy groups, clusters, and superclusters, emerged from the ceaseless gravitational attraction between galaxies, forming the intricate cosmic web that so profoundly characterizes the universe's large-scale structure today. Inside these evolving galaxies, heavier elements were tirelessly forged in the fiery hearts of stars through nuclear fusion and then scattered throughout the cosmos through spectacular supernova explosions. Imagine these stellar deaths as cosmic gardeners, seeding the universe with the very building blocks necessary for the formation of planets and, ultimately, for life itself. And the universe continues its grand journey, continuing to expand and cool, a process now known to be subtly accelerated by the mysterious influence of dark energy, a force that influences the universe's large-scale structure in ways we are only beginning to comprehend. From the very first moments after the Big Bang to the complex formation of stars, galaxies, and beyond, the universe has transformed from a uniform soup of particles into a rich, intricate tapestry woven with vast cosmic structures and hosting an incredible diversity of celestial objects and phenomena. It's an ongoing, breathtaking saga, a story still being written, inviting our constant wonder. Now let us speak more deeply of the cosmic microwave background radiation, CMBR, that faint, pervasive glow of light that fills the entire universe. Imagine it as a gentle ancient whisper, an ethereal hum, providing us with a snapshot of the cosmos as it appeared approximately 380,000 years after the Big Bang. This subtle relic radiation is truly the afterglow of the universe's formation, a direct echo dating back to a truly pivotal moment in cosmic history. This was the precise time when photons, particles of light, were first able to travel freely through space, marking the profound transition when the universe shifted from being an opaque, swirling fog to a transparent, clear expanse. It's like the mist clearing after a long, dark night, revealing the landscape for the very first time. The existence of the CMBR was a bold prediction made by cosmologists, including Ralph Alpher and Robert Herman in the 1940s, based on the Big Bang theory. But its actual discovery was famously accidental, occurring in 1965, When Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs, were troubleshooting a persistent, unexplained static noise in their large horn antenna. No matter where they pointed the antenna, or what they did to eliminate terrestrial interference, the low-level noise persisted uniformly, coming from all directions. This mysterious hum, a signal they couldn't explain, turned out to be the CMBR. Their groundbreaking finding, which earned them the Nobel Prize in Physics, provided one of the most significant and powerful pieces of evidence supporting the Big Bang theory, offering profound, direct insights into the early universe's conditions. It was the smoking gun that turned the Big Bang from a hypothesis into a widely accepted scientific model. This cosmic backdrop, this ancient glow, is remarkably uniform with a temperature of about 2.725 Kelvin, which is incredibly cold around 270.425 degrees Celsius, or 404.706 degrees Fahrenheit. Imagine a background hum almost perfectly, even across the entire sky. However, meticulous observations by sensitive space probes have revealed incredibly tiny, subtle fluctuations or anisotropies within this uniform temperature. These minute variations on the order of a few parts per million are crucial. Imagine them as tiny ripples on the surface of that primordial cosmic ocean. These ripples represent the subtle density differences that existed in the very early universe, the tiny seeds from which all the large-scale structures we see today, the galaxies, clusters, and the cosmic web, eventually grew through the relentless pull of gravity over billions of years. Space-based telescopes, such as the COBE Cosmic Background Explorer WMAP, Wilkinson Microwave Anisotropy Probe, and most recently, the highly advanced Planck satellite, have meticulously mapped these minute fluctuations in the CMBR with astonishing precision. These mappings have provided truly critical data on the universe's rate of expansion, allowing us to determine its precise age. They have also offered invaluable insights into its overall composition, revealing the relative proportions of ordinary matter, dark matter, and dark energy. Furthermore, these maps have illuminated the distribution of matter in the early universe, supporting and refining our cosmological models, painting an ever-clearer picture of our cosmic origins. The CMBR is not just an ancient echo. It is a profound cosmic message, continuously whispering secrets about the universe's past, present, and even its ultimate fate. It is a constant reminder that the universe holds deep, beautiful truths, waiting to be gently uncovered. Now, as we gently turn our thoughts from the universe's fiery beginning, let us ponder its ultimate destination. The shape and fate of the universe are deeply interconnected concepts that address its overall geometry and how it will majestically evolve over unimaginable spans of time. Imagine the universe not just as a static canvas, but as a dynamic, evolving entity, its destiny tied to its very curvature and contents. These profound ideas hinge on critical factors such as the universe's total mass-energy content and the mysterious properties of dark energy. The shape of the universe is described in terms of its overall curvature, a subtle geometric property that dictates how space itself bends. Cosmologists consider three primary possibilities, each with distinct implications. Imagine a vast, two-dimensional surface to help visualize these three shapes. First, a closed universe curves back on itself somewhat like the surface of a sphere. In such a universe, if you were to travel in a straight line for long enough, you would eventually return to your starting point, much like circumnavigating the Earth. In a closed universe, the expansion would eventually halt and reverse, leading to a big crunch. Second, an open universe curves outward like the surface of a saddle and would be endless, extending infinitely in all directions. In this scenario, the expansion would continue forever, becoming progressively colder and emptier. Third, a flat universe has no curvature at all, like a perfectly flat sheet of paper, and also extends infinitely. In a flat universe, the expansion would continue indefinitely, but would slowly approach a halt over infinite time. The geometry of the universe profoundly influences its expansion and its ultimate fate. Current observations, particularly the detailed maps of the cosmic microwave background radiation, strongly suggest that the universe is remarkably flat. This implication, if true, means that its expansion will continue indefinitely, leading to a specific kind of cosmic end. The fate of the universe is intimately tied to its shape, and crucially to the delicate balance between the density of matter, both ordinary and dark matter, which exert a gravitational pull, slowing expansion, and the mysterious force of dark energy, which seems to be accelerating expansion. In an open or flat universe, especially one influenced by dark energy, with insufficient matter to create a gravitational pull strong enough to stop its relentless expansion, the universe would continue expanding forever. Imagine a balloon being continuously inflated, growing ever larger and thinner. This scenario would lead to the universe gradually growing colder and emptier as galaxies move farther and farther apart, becoming isolated islands in an ever-increasing void. Stars would eventually burn out, leaving behind cold, dark remnants like black holes, neutron stars, and white dwarfs, which themselves would eventually evaporate or cool off. This chilling scenario is often termed the Big Freeze or heat death, where the universe ultimately becomes a vast, dark, and lifeless expanse, having reached a state of maximum entropy. In contrast, a closed universe would tell a different story. In this scenario, the gravitational pull from all its matter would eventually be strong enough to overcome the expansion. The universe would then stop expanding and begin contracting in a process known as the Big Crunch. Imagine the expansion reversing with galaxies rushing back towards each other, growing hotter and denser until ultimately collapsing into a singularity perhaps similar to the initial state of the Big Bang. This cyclical model of the universe suggests a cosmic rhythm where a big crunch might be followed by another Big Bang, leading to an endless series of expansions and contractions, a cosmic dance of creation and destruction. However, current observations strongly indicate that the universe's expansion is accelerating due to dark energy, a mysterious force that opposes gravity and pushes space apart. This groundbreaking discovery, made in the late 1990s, has significant implications for the universe's fate. It suggests that the universe will most likely continue expanding indefinitely, leading to the Big Freeze scenario described earlier. There is also the more dramatic but less favored Big Rip scenario, which posits that if dark energy continues to strengthen, it could accelerate expansion to such an extreme degree that even galaxies, stars, planets, and ultimately the atoms themselves would be torn apart. While our understanding of dark energy and the universe's total energy content is still evolving, these concepts remain central to cosmology, driving intense research efforts aimed at unraveling the mysteries of the cosmos's ultimate fate. As our technologies and theories advance, we may edge closer to understanding which, if any, of these scenarios will dictate the final majestic chapter of the cosmos. It's a grand, open-ended question, inviting us to contemplate the very last whispers of time. As we gently drift from the grand, observable scale of the universe and its cosmic ballet, let us now tiptoe into the realm of the truly theoretical, where the mind stretches beyond what we can directly see and touches upon the very deepest, most fundamental nature of reality itself. Here we encounter concepts that are not yet fully proven, but which profoundly challenge and expand our understanding of existence. Imagine stepping into a vast silent library where the most profound secrets of the universe are whispered in the language of mathematics and abstract ideas. One of the most mind-bending and captivating ideas that emerges from the extensions of modern physics theories is the concept of multiverses. Imagine it not as a single solitary universe, but rather as a vast, almost infinite collection of universes existing perhaps in parallel to our own. Each of these universes, like individual bubbles in an endless cosmic foam, could potentially have its own unique set of laws of physics, its own distinct cosmic structures, and possibly even varying constants of nature. It's a truly humbling thought, suggesting that our vast, seemingly unique universe might just be one of countless possibilities, a single note in an infinitely complex cosmic symphony. This idea, while still deeply speculative and not yet directly observable, springs from various interpretations and extensions of our most fundamental physics theories. In quantum mechanics, for instance, the famous many worlds interpretation suggests that every time a quantum event occurs, a tiny particle makes a choice or a probability wave collapses. The universe splits, creating a new parallel universe for each possible outcome. Imagine countless alternate histories and futures, all equally real, each represented by a separate universe. It's a dizzying thought where every decision, every chance branches into an entire cosmos. Meanwhile, string theory, a sophisticated attempt to reconcile gravity with quantum physics, also lends itself to the notion of a multiverse. In its intricate mathematical landscape, string theory allows for the existence of a vast landscape of possible universes within a higher dimensional space. Imagine a colossal cosmic attic filled with an unimaginable number of potential universes, each with slightly different properties waiting to be realized. This theoretical framework suggests that our universe, with its specific laws and constants, might just be one tiny valley in this immense multidimensional landscape. The multiverse theory also finds fertile ground in inflationary cosmology, which posits that during the very early moments of the Big Bang, space expanded exponentially and incredibly rapidly. This process, if it continued indefinitely in different regions, could have led to the continuous creation of countless bubble universes, each potentially budding off and growing its own unique reality, hosting different physical constants and laws. Imagine an endless foaming ocean where new bubbles continuously pop into existence, each one a universe. Although the idea of a multiverse stretches the very boundaries of empirical science, as direct evidence for other universes remains elusive, confined to the realm of theoretical physics, it offers intriguing implications for understanding some of the most fundamental questions in physics. It profoundly challenges the notion of the uniqueness of our universe, inviting us to consider a much grander scale of existence. Furthermore, it provides a possible, albeit controversial, explanation for the apparent fine-tuning of our cosmological constants, those fundamental numbers that dictate the strength of forces and the properties of particles. Why are these constants precisely what they are allowing for the existence of stars, planets, and life? In a multiverse, it's simply a matter of chance. We exist in the universe where the conditions happen to be just right for us. As such, the multiverse concept fits into modern physics as an expansive, albeit highly speculative and controversial framework that pushes the limits of science observation and our understanding of reality itself. It reminds us that the universe, in its ultimate nature, might be far vaster and more complex than our current senses or instruments, can grasp a beautiful mystery, always inviting deeper thought and profound wonder. Now let us delve into another profound and elegant theoretical framework that attempts to unravel the deepest secrets of reality string theory. Imagine the universe not as a collection of tiny point-like particles, but as a grand cosmic symphony where everything we perceive, every electron, every quark, every photon, is merely a different note played by a tiny vibrating string. This theory suggests that what we observe as fundamental particles are not infinitesimally small dimensionless points, but rather incredibly tiny one-dimensional objects. Like incredibly thin, vibrating strands of energy, the precise mode of vibration of a particular string determines the specific type of particle it appears to be. So, an electron is one vibration, a quark is another, and even the elusive graviton, the hypothetical particle that carries the force of gravity, is yet another vibration. It's a truly elegant idea, unifying all matter and forces under a single vibrating principle. String theory is considered crucial because it represents one of the most promising and significant steps towards a theory of everything toe. Imagine a single all-encompassing framework that could elegantly unite all fundamental forces and particles in a coherent, unified description of the entire universe. This is the holy grail of modern physics, the ultimate quest for intellectual coherence. The profound beauty and importance of string theory lie in its unique potential to reconcile the two seemingly disparate pillars of modern physics, quantum mechanics, which brilliantly governs the subatomic world of particles and forces at the smallest scales, and general relativity, which exquisitely explains the force of gravity and the large-scale structure of the universe. For decades, these two fundamental theories have existed side by side, each incredibly successful in its own domain, but fiercely resistant to being combined into a single seamless description. String theory offers a powerful, elegant path to bridge this profound chasm, integrating gravity naturally into a quantum framework. One of the most intriguing and often mind-bending outcomes of string theory is its bold prediction of extra dimensions beyond the four space-time dimensions that we can directly observe. We perceive 3 dimensions of space, up, down, left, right, forward, backward, and 1 dimension of time. But according to string theory, there could be as many as 6 or even 7 additional spatial dimensions curled up or compactified at scales incredibly tiny, far too small for us to detect with our current technology or senses. Imagine a garden hose viewed from afar. It looks like a one-dimensional line, but up close, you see its second curled-up dimension, its circumference. Similarly, these extra dimensions might be curled up so tightly that they are imperceptible to us. Yet, they profoundly influence the way strings vibrate, and thus, the fundamental properties of particles and forces. Despite its current lack of direct empirical evidence and the immense challenge of experimentally testing its predictions, because the energies required to probe these incredibly small scales are far beyond anything we can currently generate on Earth, string theory is considered immensely important. Its significance lies in its profound potential to explain phenomena that remain stubbornly unsolved by conventional theories such as the mysterious nature of black holes at a quantum level, or the elusive quest for the ultimate unification of all fundamental forces. It opens up entirely new lines of thinking about the fundamental structure of our universe, pushing the boundaries of knowledge and inspiring future research in both theoretical and experimental physics. It invites us to consider a reality far more intricate and multi-layered than we currently perceive, a beautiful vibrating cosmic tapestry awaiting our deeper understanding. It reminds us that the universe still holds vast silent secrets waiting for the right conceptual key to unlock them. Now let us contemplate the profound implications of quantum mechanics, a revolutionary scientific framework that has already drastically reshaped our understanding of the universe at its smallest, most fundamental scales. Imagine peering into the very building blocks of reality, where the familiar rules of our everyday world simply melt away, replaced by a realm of astonishing strangeness. Quantum mechanics, with its mind-bending principles of wave-particle duality, quantum entanglement, and superposition, tells us that reality is far more subtle and mysterious than classical physics ever imagined. Wave-particle duality suggests that tiny particles like electrons or photons can behave both as discrete particles and as spreading waves depending on how you observe them. Imagine a coin that is both heads and tails until you look at it. Superposition means that a particle can exist in multiple states or locations simultaneously until it is measured or observed, at which point it collapses into a single, definite state. It's like a ghost in multiple rooms at once until you walk in and find it in just one. And quantum entanglement is perhaps the most bewildering of all. Two or more particles can become intrinsically linked so that the state of one instantaneously affects the state of the other, regardless of the vast distance separating them. Imagine 2 dice forever linked, no matter how far apart. If one rolls a 6, the other must also roll a 6 instantly. This challenges our classical notions of local reality, space, and time, hinting at a deep interconnectedness across the cosmos. As we delve ever deeper into the strange, wondrous world of quantum mechanics, it holds the potential to further transform our understanding of the universe in several profound ways. One pivotal area is in the realm of quantum gravity. Imagine trying to build a bridge between the incredibly tiny probabilistic quantum world and the immense, smooth, continuous spacetime of general relativity. Quantum gravity is the theoretical framework that seeks to reconcile these two pillars of modern physics to describe gravity itself in quantum terms. This reconciliation, if achieved, could lead to a more complete and unified theory of gravity, potentially unlocking profound secrets about the very fabric of spacetime at its most fundamental level, the nature of black holes at quantum scales, and even offering new insights into the enduring mysteries of dark matter and dark energy. It's the ultimate intellectual frontier, promising to reshape our understanding of what reality truly is. Beyond theoretical insights, quantum computing, which harnesses the mind-bending principles of quantum mechanics, promises to revolutionize our ability to simulate incredibly complex systems. Imagine computers so powerful they can model the behavior of molecules with perfect fidelity, design new materials with unprecedented properties, or even simulate the evolution of entire universes. This could lead to truly groundbreaking discoveries in fields as diverse as medicine designing new drugs by simulating molecular interactions, material science, creating superconductors at room temperature, and even in our understanding of cosmological phenomena. Furthermore, quantum mechanics continues to raise deep philosophical questions about the very nature of reality, the role of observation in shaping what we perceive, and the fundamental limits of human knowledge. It forces us to confront uncomfortable truths. Is there an objective reality independent of our observation? Does determinism truly hold sway, or is randomness intrinsic to existence? As experiments continue to confirm, and in some cases subtly challenge aspects of quantum theory, we may need to fundamentally reconsider our views on determinism, causality, and the very notion of an objective reality. It is a constant invitation to humility and wonder. Overall, as our grasp of quantum mechanics deepens and we devise new ingenious ways to observe and manipulate the quantum world, it promises not only to provide us with revolutionary new tools and technologies, but also to offer truly profound insights into the fundamental workings of the universe at its most elementary level. It's a journey into the very heart of existence, where reality itself seems to shimmer and shift, constantly inviting us to look closer, to wonder deeper, and to embrace the beautiful inherent mystery of it all. It reminds us that the universe is far stranger and more wonderful than we can possibly imagine. Now let us confront one of the greatest and most enduring challenges in modern physics, the monumental task of uniting quantum mechanics and general relativity into a single, all-encompassing theory. Imagine two magnificent, intricately detailed maps, each perfectly describing a vast territory, one depicting the smallest, most granular details of a microscopic world, and the other charting the immense, sweeping landscapes of a colossal continent. The problem arises when these two maps simply don't align, when the rules that govern the microworld seem to contradict the rules that govern the macroworld. This fundamental difficulty arises from the profound differences in how these two theories describe the universe. Quantum mechanics, as we've explored, operates in the realm of the incredibly small, dealing with particles and forces at the atomic and subatomic levels. It is a probabilistic theory where outcomes are described in terms of probabilities rather than definite, fixed predictions. It embraces uncertainty, the idea that a particle can be in multiple places at once until observed. It describes a universe that is inherently granular, made of discrete packets of energy and matter. On the other hand, general relativity, Albert Einstein's magnificent theory, governs the large-scale structure of the universe. It describes gravity not as a force acting across space, but as the curvature of spacetime itself, caused by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip, and other marbles rolling nearby are drawn into that dip. General relativity treats spacetime as a smooth, continuous, and flexible fabric a seamless continuum. One significant hurdle in uniting these two visions is this very conceptual difference. Quantum mechanics suggests a discrete, quantized nature of phenomena, where everything comes in tiny, indivisible packets, while general relativity treats space-time as a smooth, unbroken continuum. This poses a deep conceptual challenge in imagining a quantum theory of gravity, where space-time itself would have a quantum structure possibly made of tiny, indivisible units, perhaps something akin to space-time atoms or a quantum foam. How can a smooth, continuous fabric emerge from discrete, probabilistic quanta? This is the central enigma. Another issue is that general relativity is a classical theory, meaning it does not inherently include the principles of uncertainty and superposition that are so fundamental to quantum theory. When physicists attempt to apply quantum rules to the gravitational field, using conventional methods, their calculations frequently lead to perplexing mathematical inconsistencies, often yielding infinities that cannot be easily removed or reconciled. It's like trying to combine two different languages with different grammatical rules, resulting in nonsensical sentences. Additionally, while experiments have confirmed the astonishing predictions of quantum mechanics and general relativity in their respective domains with incredible accuracy, a testament to their power, testing theories that attempt to unify them, such as string theory or loop quantum gravity, is exceedingly difficult with current technology. The unification is predicted to occur at incredibly small scales, far smaller than an atomic nucleus, and incredibly high energies far beyond what even the most powerful particle accelerators can generate. This means direct experimental verification remains elusive, making it challenging to choose between competing theoretical frameworks. The pursuit of a unified theory, often referred to as quantum gravity, requires not just bridging the mathematical gap between the theories, but also a profound conceptual shift in our understanding of space-time matter and the very fabric of reality itself. It invites us to rethink our most basic assumptions about existence. Bridging this profound divide not only promises to unlock some of the deepest secrets of the universe, from the true nature of black holes to the very first moments of the Big Bang, but also to redefine fundamental physics as we know it, painting a new, more complete picture of the cosmos. It's a quiet, persistent quest for intellectual harmony, a testament to humanity's unending curiosity about the deepest truths of the universe. As we slowly pull our gaze back from the abstract wonders of theoretical physics, let us now turn our minds to a more tangible, yet equally awe-inspiring aspect of our cosmic story. Humanity's own relentless journey outwards, our persistent quest to reach for the stars. This is where our dreams of discovery meet the very real challenges of technology, physiology, and ingenuity. Imagine our species like tiny boats on a vast ocean, constantly striving to sail further into the unknown. The future of space travel is truly poised to be revolutionized by several emerging technologies, each holding the potential to overcome the current limitations of cost, speed, and efficiency that have long tethered us to our home planet. Imagine building faster, more resilient ships for the cosmic ocean designed to carry us further and with greater ease. One of the most anticipated and transformative technologies is nuclear propulsion, a concept that could drastically reduce travel time within our solar system. Unlike conventional chemical rockets, which rely on the rapid combustion of propellants, nuclear propulsion systems such as nuclear thermal or nuclear electric designs offer much higher efficiency and thrust for the amount of fuel carried. Imagine cutting the arduous multi-month journey to Mars by half or even more, making human missions to the Red Planet not just possible, but genuinely feasible and safer for astronauts. These systems, harnessing the immense power of atomic nuclei, promise to unlock speeds and durations previously confined to the realm of science fiction. Another groundbreaking technology that is already reshaping the landscape of space travel is the relentless development of reusable rockets, brilliantly pioneered by companies like SpaceX. Imagine a ship that, after delivering its cargo, can gracefully land itself back on Earth, ready to be refueled and launched again, much like an airplane. This innovation profoundly reduces the cost of access to space by allowing the same spacecraft components to be launched, landed, and reused multiple times. This paradigm shift makes space travel exponentially more economically viable, opening the door for more frequent missions, larger payloads, and a broader array of participants in the cosmic journey. It's a fundamental change, moving from a disposable model to one of sustainability and efficiency. On the horizon, though, still firmly in the realm of ambitious concepts, are space elevators. Imagine a colossal tether extending from the Earth's surface directly into geostationary orbit. While currently limited by the incredible strength and material science required to build such a structure space, elevators could revolutionize space travel by providing a continuous energy-efficient means to transport materials and people to space, bypassing the need for costly, fuel-intensive rocket launches entirely. It would be like building a bridge to the heavens, offering a gentle, almost seamless ascent into orbit. Beyond propulsion and launch systems, advanced materials and manufacturing techniques are also dramatically improving spacecraft design. Imagine materials that are incredibly strong, yet remarkably lightweight, or even skins that can heal themselves in the harsh vacuum of space. The integration of cutting-edge composites, ceramics, and alloys is crucial. Furthermore, the advent of 3D printing in space, known as in-space manufacturing, would enable the construction of spacecraft components, habitats, and tools directly in orbit or on other celestial bodies using local resources. This would dramatically reduce the immense logistical challenges and costs associated with launching everything from Earth, further lowering costs and expanding the possibilities for long-duration space missions and even colonization efforts. Finally, quantum communication technology promises to enhance secure and ultra-fast communication across the vast distances in space. Imagine signals that cannot be intercepted or disrupted, allowing for more sophisticated and responsive exploration missions and potentially enabling truly real-time human presence and interaction on other planets, overcoming the frustrating light-speed delays we currently face. As these and other nascent technologies continue their remarkable progress, they promise not only to vastly expand our reach within the solar system, but also to fundamentally transform our understanding of travel and life in space, making the cosmos more accessible, more manageable, and more intimately connected than ever before. It's a future where the distant dreams of today become the routine realities of tomorrow. Now, as our advanced technologies push the boundaries of distance and speed, we must also humbly acknowledge the inherent limits of human exploration in space for our bodies. Though resilient, are delicate vessels designed for Earth's gentle embrace. These limits are governed by a complex interplay of technological, physiological, and economic factors, each posing its own unique challenges. From a technological standpoint, the sheer vastness of distances between celestial bodies remains a formidable hurdle. Even the nearest stars are light years away. A light year is the distance light travels in 1 year, an unimaginable 9.5 trillion kilometers. This means that reaching even the closest stars, let alone other galaxies, would require propulsion systems far, far beyond our current capabilities for any feasible human travel within a single lifetime. While we can send robotic probes on multi-decade journeys to the outer solar system, a human mission demands a vastly different timeline and resource commitment. Moreover, the harsh conditions of space itself, including extreme temperatures ranging from searing heat to absolute zero, the crushing vacuum of space, and the relentless onslaught of cosmic radiation, necessitate incredibly advanced life support and protection technologies. These systems must be meticulously engineered to sustain human life and well-being for extended periods, creating miniature Earths within the cold, unforgiving void. Physiologically, the human body faces significant and often debilitating challenges in the microgravity environment of space. Imagine muscles slowly wasting away and bones gradually losing their density, as if our bodies are forgetting how to exist without gravity's constant pull. Astronauts experience muscle atrophy and bone density loss, which can be severe over long durations. Furthermore, prolonged exposure to harmful space radiation, primarily from solar flares and galactic cosmic rays, poses a serious long-term health risk, increasing the likelihood of cancer and other ailments. These physiological factors fundamentally limit the duration astronauts can safely spend in space without suffering serious, irreversible health consequences. Effective countermeasures, such as rigorous exercise regimes, advanced nutrition, and robust radiation shielding, or revolutionary technologies, are critical for longer missions, such as those ambitious journeys to Mars or beyond where astronauts would be in space for years. Economically, the costs associated with space exploration are truly staggering, measured not in millions, but in billions and even trillions of dollars. Developing, launching, and meticulously maintaining complex missions require substantial financial investment, drawing from national budgets and often demanding international collaboration. Imagine the immense resources required to build a single spacecraft capable of safely transporting humans to Mars and back, let alone establishing a sustainable colony. This makes it crucial for nations and organizations to carefully balance ambitious scientific aspirations with available resources, often leading to difficult choices and trade-offs. While the increasing involvement of the private sector has introduced new funding streams and a burst of innovation, the sheer financial demands of overcoming these profound technological and physiological barriers continue to be a significant limiting factor, shaping the pace and scale of our cosmic ambitions. Despite these immense limitations, the intrinsic human drive to explore and understand our universe persists, an unwavering flame of curiosity that continuously pushes the boundaries of human capability and technology. Ongoing advancements in propulsion like nuclear or even more exotic methods, life support systems and habitat design, combined with growing international cooperation and innovative public-private partnerships, offer promising pathways to extend the reach of human exploration in space. We are constantly pushing against these limits, slowly but surely, expanding our presence and understanding in the cosmos. It's a testament to the enduring human spirit, always looking upwards, always wondering what lies beyond the next horizon, and always finding new ways to reach for it. Now let us turn our attention to the remarkable advancements in spacecraft design, which are dramatically propelling humanity further into the cosmos. Imagine these machines as elegant, sophisticated extensions of our will, each a masterpiece of engineering, material science, and computational technology. These are not merely vehicles. They are the finely tuned instruments of our cosmic aspirations. One of the most standout and truly transformative developments is the increasing use of reusable spacecraft, exemplified brilliantly by SpaceX's Falcon rockets and Dragon capsules. Imagine a giant multi-stage rocket that, after sending its payload into orbit, can land its first and even second stages gently back on Earth upright, ready to be refueled and relaunched. These revolutionary systems fundamentally reduce the cost of access to space by allowing for the recovery and reuse of expensive launch vehicles, a true paradigm shift from the traditional single-use rockets that were discarded after each mission. This makes space travel exponentially more economical, opening the door for more frequent missions, larger payloads, and a wider array of participants in the cosmic journey, from commercial ventures to scientific explorations. Another cutting-edge technology in spacecraft design is the relentless development of more efficient propulsion systems. While chemical rockets provide immense thrust for launch, they are less efficient for long-duration interplanetary travel. Here, ion thrusters emerge as a fascinating alternative. Imagine a gentle, continuous push from electrically charged particles, offering incredibly fuel-efficient propulsion, though with less immediate thrust than a chemical rocket. These are ideal for long, slow journeys like robotic probes to distant planets, steadily building speed over months or years. Research is also vigorously underway on nuclear thermal propulsion, which, as we discussed, could provide a significantly higher thrust-to-weight ratio than chemical rockets, drastically reducing transit times to Mars and beyond, making human interplanetary travel far more feasible and safer. Advancements in material science are also absolutely critical to pushing the boundaries of spacecraft design. Imagine new materials that are incredibly strong, yet remarkably lightweight, or even smart skins that can detect and repair micrometeoroid damage. The integration of cutting-edge lightweight composite materials, durable ceramics, and self-healing skins is revolutionizing how spacecraft are built. These advanced materials can withstand the incredibly extreme conditions of space travel, from the searing heat of re-entry to the frigid vacuum from intense radiation exposure to micrometeoroid impacts, all while significantly reducing the overall weight of the spacecraft. A lighter spacecraft means less fuel is needed, which translates to lower costs and greater capabilities. Artificial intelligence, AI, and robotics are playing increasingly prominent roles, acting as the intelligent nervous system of modern spacecraft. Imagine autonomous systems that can navigate complex terrain on Mars without human intervention, or robots that can perform intricate repairs far from Earth. AI facilitates autonomous navigation onboard decision-making crucial when light-speed communication delays make real-time human control impossible and even sophisticated systems maintenance. This reduces the need for constant ground control intervention and dramatically increases the resilience and efficiency of missions in the deep space environment. AI-driven robotics could also play a central role in constructing habitats and infrastructure on other planets, performing tasks in environments too dangerous or impractical for humans. Lastly, the concept of inflatable habitats and modules, such as those being developed by companies like Bigelow Aerospace, represents a remarkable leap forward in creating livable spaces for astronauts. Imagine a compact module that launches inside a rocket, then expands to many times its size, once in orbit or on another celestial body. These habitats can be compactly transported and then expanded once in orbit or on another celestial body, providing significantly more volume and comfort for crew members than rigid metal modules. These advanced spacious habitats could play a crucial role in long-duration missions, enhancing astronaut well-being and productivity. Together, these technologies are not just incrementally improving space exploration. They are fundamentally expanding the possibilities, making the dream of sustainable human presence in space and the exploration of far-off worlds more attainable than ever before. It's a quiet revolution shaping our future among the stars. As we quietly ponder the marvels of advanced spacecraft and the immense challenges of pushing human limits, our thoughts inevitably turn to one of the most profound and perhaps most ancient questions that stirs within the human heart. Are we alone? This is the whisper that accompanies us as we peer into the night sky, a longing for connection across the silent void. This chapter gently guides us through the dedicated search for life beyond Earth, both within our familiar solar system and in the distant, dazzling realms of exoplanets, where conditions may just be right for life to unfurl its miraculous banner. The quest to discover life beyond Earth focuses on specific locations, both within our own solar system and beyond, where conditions may be just right for life as we understand it, to take root and flourish. Imagine us as cosmic detectives meticulously searching for clues in the vast, silent stretches of space. One of the most tantalizing prospects, and perhaps our closest cosmic sibling in this regard, is Mars. Picture the red planet. Now a cold, dusty desert, but carrying whispers of a vibrant past. Evidence of ancient riverbeds, the presence of minerals that form in water and reservoirs of water ice beneath its surface all strongly suggest that liquid water once flowed freely across its landscape for extended periods. This raises the profound possibility that life could have existed there in the past, perhaps in warm, mineral-rich pools. Even more thrilling, scientists speculate that life might still exist today in protected niches beneath the surface, shielded from the harsh radiation and extreme temperatures, perhaps thriving in underground aquifers or within sheltered geological formations. The ongoing exploration by rovers like Curiosity and Perseverance is a testament to this persistent hope, tirelessly drilling and analyzing samples for any telltale signs. Equally intriguing are the icy moons of Jupiter and Saturn, Europa, Enceladus, and Titan. Imagine these as frozen jewels seemingly lifeless on their surfaces, but harboring deep dark secrets within. Each of these captivating moons is believed to harbor vast subsurface oceans beneath their thick icy crusts. On Europa, the immense tidal forces from Jupiter's gravity likely keep a vast ocean warm and churned, potentially hosting hydrothermal vents on its seafloor, similar to those that support thriving ecosystems in Earth's deep oceans entirely without sunlight. On Enceladus, as we briefly mentioned, direct evidence comes from spectacular geysers of water vapor and ice particles erupting from fissures in its south pole, hinting at an active, warm ocean communicating with space. Titan, Saturn's largest moon, with its thick atmosphere and liquid methane lakes, offers a glimpse of an alien chemistry that might still support a form of life, even if radically different from our own. These subsurface oceans represent incredibly compelling candidates, where life could exist, protected from the harshness of space in environments vastly different from our own, yet potentially teeming with hidden life. Beyond our immediate solar system, the search broadens dramatically to exoplanets, those distant worlds orbiting stars far beyond our sun. Here, the focus is on planets situated within the habitable zones of their respective stars. Imagine searching for countless cosmic Goldilocks planets, where the conditions are neither too hot nor too cold for liquid water to exist on their surfaces. Planets like Proxima Centauri b, orbiting our nearest stellar neighbor Proxima Centauri, offer tantalizing possibilities. Its location within the habitable zone of its dim red dwarf star hints at the potential for liquid water on its surface, a key ingredient for life as we know it. These celestial bodies, each with unique environments, represent the very forefront of our search for life, guiding our exploration with the profound promise of uncovering not just new worlds, but possibly new forms of life, fundamentally expanding our understanding of what it means to be alive in the cosmos. It's a quiet, persistent quest, fueled by curiosity and hope. Now let us imagine the profound moment, the proof of life beyond Earth. This would undoubtedly be a milestone in human understanding, a seismic shift in our perception of ourselves and our place in the universe. Such a monumental discovery would require incontrovertible evidence that could withstand the most rigorous scrutiny of the global scientific community, leaving little to no room for doubt. Imagine a clear, undeniable signal that reshapes our cosmic narrative. The form of this evidence could vary dramatically depending on where and how we search. For instance, if examining the surface of Mars, the discovery of microbial fossils unmistakably embedded in rock formations, fossils that mirror the earliest forms of life found on Earth with clear cellular structures and unambiguous signs of biological activity, would provide tangible and compelling proof of past life. Imagine finding the ancient imprints of tiny alien beings preserved for eons in the red Martian soil. Scientists would look for complex organic molecules, clear evidence of metabolism, and structures that could only be explained by biological processes. In the tantalizing subsurface oceans of our solar system's icy moons, like Europa or Enceladus, the evidence might come from analyzing plumes of water ejected into space. Imagine a robotic probe flying through one of Enceladus's geysers, capturing samples directly from its hidden ocean. The analysis of these samples might reveal the presence of complex organic compounds arranged in patterns indicative of life, or even the direct detection of microbial life itself. Living organisms that inhabit these deep, dark subsurface oceans. This would be a direct, chilling, and utterly breathtaking encounter with alien life. The detection of self-replication or specific metabolic pathways within these samples would provide powerful confirmation. In the case of exoplanets, worlds beyond our solar system, direct evidence remains incredibly challenging to obtain. with current technology due to their vast distances. Here, the proof may be more indirect, yet still highly compelling, derived primarily from the meticulous analysis of atmospheric compositions using spectroscopy. Imagine filtering the faint light from a distant star through the thin veil of an exoplanet's atmosphere, looking for specific chemical fingerprints. The detection of certain biosignature gases, such as abundant oxygen, which is highly reactive and usually consumed by geological processes, unless constantly replenished by life ozone, a byproduct of oxygen, methane, and carbon dioxide, in the right proportions and out of chemical equilibrium, could strongly suggest the presence of biological processes on that distant world. For example, finding large amounts of both oxygen and methane simultaneously in an atmosphere is a strong indicator of life, as these gases tend to react with each other and wouldn't persist together without continuous biological production. Ultimately, the proof of extraterrestrial life would likely require a combination of findings, a layered accumulation of evidence that paints an undeniable picture. This would include direct evidence such as actual microorganisms or their unique biochemical signatures, like specific proteins or DNA-like structures not found anywhere else, complemented by indirect evidence such as atmospheric biosignatures or clear large-scale alteration of a planet's surface or chemistry that could only be explained by the pervasive influence of living organisms. This multi-pronged approach would help build an increasingly compelling case, gradually leaving little room for doubt that we are not alone in the universe. It would be a moment that transcends science, reshaping our philosophy, our understanding of life itself, and our place in the cosmic story forever. The search for extraterrestrial life is far more than a mere scientific endeavor. It is a profound and captivating quest that profoundly shapes the human imagination, weaving its intricate way into the very cultural and scientific fabric of society. Imagine it as a timeless story whispered across generations, fueled by an insatiable curiosity about the unknown. This quest directly challenges our deepest understanding of life, of existence, and of our unique place in the universe, fostering a boundless sense of wonder and awe. This intellectual journey, while primarily driven by scientific inquiry, gently spills over into the profound realms of philosophy, theology, and ethics. It prompts us to confront fundamental questions that have resonated throughout human history. What is consciousness? What defines intelligence? Is communication with non-human entities truly possible? And what form might it take? It forces us to reconsider the very definition of life itself, stretching beyond our earthbound biases. On a practical level, the relentless pursuit of life beyond Earth yields tangible benefits for our own planet. Imagine new technologies, new insights, all born from the desire to look outwards. The technologies developed and the immense knowledge gained from this search have profound and often unforeseen positive impacts for Earth, including remarkable advancements in fields as diverse as astrobiology, the study of life in the universe, chemistry, understanding the building blocks of life under extreme conditions, environmental science, learning how life adapts to different planetary conditions, informing our stewardship of Earth, and even robotics and artificial intelligence. This beautifully demonstrates the deep interconnectedness of Earth's complex ecosystems with the wider cosmos, showing us that by looking out, we often learn more about ourselves and our home. Moreover, the pursuit of life beyond Earth serves as a powerful unifying endeavor, transcending national, cultural, and ideological boundaries. Imagine scientists and engineers from diverse backgrounds, all working together towards a shared, inspiring goal. It reminds us of our common heritage as inhabitants of this pale blue dot and our shared destiny in the vastness of space, fostering a profound sense of planetary stewardship and the urgent need to protect our precious home world, even as we reach for the stars. The scale of the universe humbles us, reminding us that our differences on Earth are tiny in comparison to the immense cosmic stage. The implications of discovering extraterrestrial intelligent life would be nothing short of revolutionary. Imagine the news rippling across the globe, transforming our understanding of biology, chemistry, and physics overnight. It would fundamentally revamp the social sciences as we grapple with alien societies' communication and ethics. It could even subtly affect everyday life through the emergence of new technologies inspired by alien insights or by profoundly shifting our philosophical perspectives on life's meaning and purpose. In sum, the search for extraterrestrial life is far more than a scientific endeavor. It is a profound reflection of humanity's insatiable quest for knowledge and our unyielding drive to explore the unknown. It holds a mirror to our collective soul, highlighting our deepest fears and highest aspirations, and reminding us of the boundless possibilities that lie within the universe. It is a continuous invitation to wonder, to dream, and to humbly accept our place in a cosmos that may be far more populated and astonishing than we currently dare to imagine. Now let us imagine the profound moment, the discovery of extraterrestrial microbial life. This would mark a truly profound moment in human history, a gentle yet seismic shift that would reshape our understanding of biology, chemistry, and the very essence of life itself. Such a discovery would confirm beyond a shadow of a doubt that Earth is not the only crucible of life in the universe. Imagine the immensity of that realization. Life is not a unique, isolated phenomenon, but rather a universal principle capable of emerging under the right conditions in countless cosmic settings. This would significantly increase the likelihood that life exists in many forms across the cosmos, from the simplest microbes to potentially complex ecosystems. This revelation would have immediate and far-reaching implications for the burgeoning field of astrobiology. Imagine astrobiology previously confined to theoretical models and Earth-based extremophiles suddenly gaining its very first real-world extraterrestrial subject. This would catalyze an unprecedented surge in research, directing the search for more complex forms of extraterrestrial life and profoundly guiding our future exploration of other planets and moons. We would no longer be guessing where to look. We would have a confirmed example, a direct reference point for life beyond our planet, informing every future mission and every scientific inquiry. The discovery would also prompt a thorough and often challenging re-examination of the theory of life's origins. Scientists would delve deeply into questions about whether life on Earth and elsewhere shares a common ancestry, perhaps through a process like panspermia, where life might have been transported between worlds via meteorites. Or perhaps life emerged independently under remarkably similar conditions on different worlds, suggesting a universal recipe for life that applies across the cosmos. This would profoundly influence our understanding of how life might evolve in vastly different environments, offering invaluable insights into the incredible resilience and adaptability of life pushing the boundaries of what we thought was possible. From a societal perspective, the knowledge that we are not alone, even if the others are merely microbes, would likely alter the very foundations of our philosophical, theological, and existential frameworks that have been in place for millennia. Imagine the quiet shifts in human thought as our anthropocentric view of the universe begins to recede. It would invite dialogue and reinterpretation within and among religions, prompting contemplation about the place of extraterrestrial life in creation, and how such discoveries align with or challenge spiritual beliefs. The knowledge that life can thrive in environments vastly different from our own could profoundly expand the human perspective, challenging us to consider our place in the universe anew with humility and a renewed sense of interconnectedness. Such a discovery would also have practical implications for future space exploration. It would profoundly influence how missions are planned and conducted, emphasizing even more stringent planetary protection protocols to avoid biological contamination between worlds. We would need to ensure that we don't accidentally transport Earth microbes to pristine alien environments or vice versa to preserve the integrity of both potential ecosystems and our scientific investigations. It would also raise new ethical considerations about the protection of extraterrestrial ecosystems and whether humanity has the right to interfere with them even if they are only microbial. In some, finding extraterrestrial microbial life would be a powerful catalyst for scientific, philosophical, and cultural evolution, marking a monumental step in the ongoing human quest to understand the cosmos and our profound place within it. It's a quiet whisper from the stars, confirming a truth we have long suspected and forever changing the way we see ourselves. Now let us dare to imagine an even more profound scenario: the discovery of intelligent alien life. This would undoubtedly elicit a wide range of deeply complex reactions across humanity, stirring a truly intricate tapestry of emotions, thoughts, and responses. Imagine the ripples spreading across the globe, touching every mind, every heart, every corner of human existence. Initially, there might be a profound sense of awe and wonder, an almost spiritual experience at the realization that we are definitively not alone in the universe. This would be accompanied by an overwhelming surge of curiosity about these other beings. How do they live? What are their societies like? What is their technology? What is their understanding of the universe? This singular revelation could potentially unite humanity in a shared sense of purpose and collective curiosity, momentarily bridging existing divides and conflicts as we face the overwhelming reality of a larger cosmos bustling with intelligence. It could be the ultimate catalyst for global unity, a shared adventure for all of mankind. Simultaneously, however, the discovery could very well invoke a deep sense of apprehension and fear about the unknown. Imagine the natural human instinct to be cautious when encountering something entirely new and powerful. Questions would arise about their intentions. Are they benevolent visitors or potential threats? What are their capabilities, their technology, their values? Long-held beliefs and narratives about human uniqueness and our central place in the universe would be fundamentally challenged, forcing a profound period of introspection and re-evaluation. Religious and spiritual beliefs across the globe could undergo a period of intense inspection and reinterpretation in light of this new knowledge, prompting dialogue about the place of extraterrestrial intelligence in creation and how such discoveries align with or challenge existing spiritual frameworks. On a scientific and technological level, there would likely be an unprecedented global push to learn more about these beings. Imagine every scientific discipline dedicating its resources to this singular goal. How do they communicate? What are their social structures and cultures? What are the principles behind their advanced technology? What is their understanding of the universe's deepest mysteries? This relentless quest for knowledge could powerfully drive international collaborations, fostering a new era of unprecedented technological innovation, all inspired by the profound desire to communicate with or even someday visit these extraterrestrial intelligences. It would redefine what is possible for our own species. Governments and international organizations would inevitably grapple with immense issues of diplomacy and governance in this broader cosmic context. Imagine the intricate discussions about how to establish guidelines or protocols for interaction with non-human intelligences. What would be our first message? What information should we share? The principles of such interstellar diplomacy would be entirely uncharted territory, requiring careful thought and profound wisdom to avoid misunderstandings or conflicts. It would force humanity to define its own values and intentions on a cosmic scale. Ultimately, the discovery of intelligent alien life would mark a truly pivotal point in human history. It would challenge us not just to expand our scientific and technological perspectives, but to profoundly reconsider our place in the cosmos. It would prompt not just scientific inquiry, but a deep cultural and psychological shift as humanity comes to grips with the reality of other intelligent beings in the universe. It's a dream that holds both immense promise and profound uncertainty, a true testament to the universe's endless capacity to surprise and humble us. Now let us meditate on the even deeper, more subtle implications. The philosophical implications of discovering life elsewhere in the universe are profound and multifaceted. Inviting a re-evaluation of some of humanity's most foundational questions and beliefs. Imagine looking into a cosmic mirror and seeing not just your own reflection, but echoes of life from across the stars. Firstly, the very existence of extraterrestrial life, and especially intelligent life, directly challenges the deeply ingrained anthropocentric view. The belief that humans are the central or most significant entities in the universe, that we are unique and singularly important. It gently prompts a reconsideration of human exceptionalism, urging us to see ourselves not as the pinnacle of cosmic creation, but as a part of a broader, unimaginably vast tapestry of life that spans the cosmos. It's a humbling thought, expanding our sense of belonging to something much, much larger. Secondly, the discovery would breathe vibrant new life into age-old philosophical inquiries about the nature of consciousness, intelligence, and the profound potential for communication and understanding across species boundaries of a cosmic scale. Imagine trying to bridge the gap between radically different forms of thought and perception. It would provoke deep questions about whether human modes of thought perception and reasoning are truly unique, or if they share fundamental commonalities with those of other intelligent entities. What does it mean to think? What defines true intelligence? These are questions that would take on an entirely new urgency and depth. Ethical considerations would also surge to the forefront, particularly regarding our responsibilities toward other life forms. Imagine creating a new universal ethic. The discovery could lead to the profound expansion of ethical theory to include not just all humans or even all terrestrial life, but all sentient beings in the universe. This universalist perspective might profoundly influence how we treat other species on Earth and guide our interactions with extraterrestrial life, underpinning them with a recognition of the intrinsic value of consciousness and sentience wherever it exists. Whether it be a microscopic organism or a highly advanced civilization, it forces us to define what it means to be a moral agent on a cosmic scale. Moreover, the existence of life elsewhere would undoubtedly have significant theological implications, challenging or requiring reinterpretation of religious doctrines that are centered on human beings and Earth as the sole focus of creation. Imagine a profound dialogue among and within religions about the place of extraterrestrial life in creation and how such discoveries align with or challenge existing spiritual beliefs. This would necessitate a deeper, more expansive understanding of faith and existence. In essence, the discovery of extraterrestrial life would act as a powerful philosophical catalyst, propelling humanity into an expansive reflection about our understanding of life, intelligence, morality, and our fundamental place in the cosmos. It represents an unparalleled invitation to broaden our horizons, to shed our provincial views, and to humbly embrace a more truly cosmic perspective on existence, one that recognizes the boundless wonders and profound connections that extend far beyond our blue world. It's a journey not just into space, but into the very depths of our own understanding. As we quietly ponder the marvels of advanced spacecraft and the immense challenges of pushing human limits, our thoughts inevitably turn to the future. A future shaped by our ambitions, our ethics, and our ever-growing capacity to reach for the stars. This final chapter gently explores humanity's ongoing venture into the cosmos, pondering not just where we might go, but how we might go, and what responsibilities we carry with us into the vast unknown. The ambitious goal of colonizing other planets is no longer mere science fiction. It is a profound aspiration that humanity is progressively working towards, driven by remarkable advancements in technology and a constantly deepening understanding of our solar system. Imagine humanity establishing new outposts, new homes on distant worlds. While the concept of establishing human colonies beyond Earth presents undeniably significant and daunting challenges, it is increasingly seen as feasible within the coming decades, particularly with a focused eye on our nearest celestial neighbors like Mars and the Moon. The very feasibility of extraterrestrial colonization hinges on overcoming monumental obstacles, each requiring immense ingenuity and sustained effort. Foremost among these is the fundamental provision of sustainable life support systems. Imagine creating a miniature self-contained earth recycling air, water, and waste in a closed loop, endlessly providing for human needs in a hostile environment. This includes developing robust systems for oxygen generation, water reclamation, and food production in environments utterly devoid of Earth's natural life-sustaining processes. Crucially, we must also devise effective protection from cosmic radiation, a relentless barrage of energetic particles from the sun and deep space that poses a severe threat to human health over long durations. Furthermore, the profound psychological effects of long-duration isolation and confinement in extreme environments must be meticulously addressed, ensuring the mental well-being of colonists far from home. In addition to these life-sustaining systems, the development and transportation of the necessary infrastructure and supplies to support human life in the vastly different environments of other planets is a truly daunting logistical task. For Mars, for instance, solutions for producing oxygen, water, and food from local resources are paramount. We must also develop advanced shielding materials to protect habitats from radiation and micrometeoroid impacts, and create propulsion systems powerful and efficient enough for the journey itself. Technological innovations and relentless research in fields such as closed-loop life support systems in situ, resource utilization, ISRU habitat construction, and space farming are all key areas that could significantly increase the feasibility of planetary colonization. ISRU in particular is pivotal. Imagine using Martian soil to 3D print building materials or extracting precious water ice from lunar craters to create breathable air and rocket fuel. This process, involving the utilization of local resources on other celestial bodies, dramatically reduces the costs and logistics of transporting every single item from Earth, making long-term settlements far more sustainable. The increasing involvement of both governmental space agencies such as NASA, ESA, and Roscosmos, and pioneering private companies like SpaceX and Blue Origin has significantly accelerated the pace towards making space colonization a more tangible possibility. SpaceX's ambitious development of the Starship spacecraft, for instance, is aimed directly at making human life multiplanetary, with Mars as its initial target. In summary, while colonizing other planets remains an immense challenge, ongoing advancements in space technology and a growing concerted international interest in space exploration are steadily making the prospects of establishing permanent human settlements beyond Earth more feasible than ever before. The combination of technological breakthroughs, deeper physiological understanding, and careful psychological considerations will be key to overcoming the remaining barriers, gently guiding humanity towards becoming a multiplanetary species, a future where our footsteps may echo on distant sands. As humanity reaches further into the cosmos, the journey is not without its footprint. Space exploration, while pushing the boundaries of human knowledge and capabilities, inherently carries with it environmental impacts that are both direct and indirect. Imagine a beautiful, pristine canvas, subtly marked by our expanding presence. One of the primary and most pressing concerns is the growing amount of debris left in Earth's orbit, commonly known as space junk. Picture a swirling cloud of defunct satellites, spent rocket stages, and countless fragments from disintegrations, erosion, and collisions, some as tiny as a paint fleck, others as large as a bus. This ever-increasing clutter poses significant risks to operational satellites, the International Space Station, and future space missions. Imagine a tiny piece of debris traveling at tens of thousands of miles per hour, capable of inflicting catastrophic damage. This risk can potentially trigger a cascading chain reaction of collisions, famously known as the Kessler syndrome, where each collision generates more debris, leading to an exponential increase in orbital junk and making low Earth orbit unusable. On Earth, the launching of rockets also contributes to both air and water pollution. Rocket propellants, while incredibly powerful, can release various substances into the atmosphere, some of which, like chlorine and alumina particles, can contribute to ozone layer depletion or alter atmospheric chemistry. Additionally, the immense impact of building and maintaining sprawling launch facilities, often located in pristine or ecologically sensitive areas, can disrupt local ecosystems and wildlife, requiring careful environmental management and mitigation efforts. However, it is important to acknowledge that the space community is increasingly aware of these environmental issues and is actively working towards more sustainable practices. Imagine a concerted effort to minimize our footprint even as we reach for the stars. This includes dedicated efforts to design more sustainable rocket technologies, focusing on cleaner fuels and more efficient combustion. Plans for debris removal are being meticulously researched and developed, aiming to actively clean up the orbital environment. Furthermore, the development of robust international guidelines and best practices aims to minimize and mitigate environmental impacts throughout the entire life cycle of space missions, from launch to end-of-life disposal of satellites. As space exploration advances, balancing the profound quest for discovery with responsible environmental stewardship remains a critical challenge, underscoring the deep need for sustainable practices in our magnificent journey among the stars. It's a testament to our growing awareness that our cosmic ambitions must be tempered with earthly responsibility. The future of the International Space Station ISS, that magnificent emblem of international cooperation and enduring scientific achievement, gracefully orbits around evolving space exploration goals and the shifting currents of geopolitical dynamics. Imagine it as a grand floating laboratory, a testament to what humanity can achieve when working together, but also a structure with a finite lifespan. Currently, the ISS is formally approved for operation until 2024, with ongoing discussions among its partner nations, the United States, Russia, Japan, Europe, and Canada, about extending its operational life until 2028 or even beyond. As this complex aging orbital outpost continues its long service, maintaining its safety, functionality, and scientific utility will undeniably require significant ongoing investment in maintenance, repairs, and technological upgrades. It's like maintaining a beloved intricate machine requiring constant care. Beyond the immediate future of the current ISS, there is a growing and undeniable interest in transitioning from this state-operated model to a more commercial one. Imagine private companies stepping in, not just as contractors, but as owners and operators of orbital platforms. In this vision, private companies could eventually take over operations using the ISS or successor platforms for a wide range of commercial activities, including advanced research and manufacturing in microgravity space tourism, and even as platforms for future deep space missions. This approach could potentially pave the way for a dynamic new era of privately run commercial space stations, opening up access to space for a much wider array of non-governmental users. Simultaneously, several countries and private entities have already expressed strong interest in developing their own independent orbital platforms. Imagine a new generation of space stations, perhaps specialized for specific scientific, commercial, or exploratory goals, fostering a competitive yet collaborative environment in low Earth orbit. In the meantime, NASA and its international partners are increasingly looking beyond low Earth orbit towards the Moon and Mars. They are planning to leverage the invaluable knowledge, operational experience, and technological advancements gained from the decades of operating the ISS to build sustainable outposts for long-duration human missions to lunar orbit and the lunar surface, and eventually to Mars. The profound legacy of the ISS, particularly in terms of fostering unprecedented international collaboration and conducting groundbreaking scientific research in microgravity, will undoubtedly influence and inspire future endeavors in space. It has shown us what is possible when nations work together towards a common, inspiring goal. As humanity continues to reach beyond the comfortable confines of our home planet, the ISS stands as a powerful symbol of our collective aspirations, a testament to human ingenuity and the enduring spirit of cooperation in the pursuit of cosmic knowledge. Its journey may be nearing its end, but its lessons will echo throughout the future of human space exploration. Now let's explore a pivotal frontier in our journey beyond Earth advances in propulsion technology. Imagine the universe as a vast, shimmering ocean, and our spacecraft as ships. The speed and efficiency of these ships determine how far and how quickly we can sail. Traditional chemical rockets, while incredibly powerful for lifting payloads off Earth, have inherent limitations in efficiency and speed for long-duration interplanetary missions. They are like powerful but fuel-thirsty engines, making journeys to Mars and beyond dauntingly long and resource-intensive challenges. The development of new propulsion methods promises to dramatically reshape the landscape of space exploration, unlocking possibilities that were once firmly in the realm of science fiction. Imagine a continuous gentle push that accelerates a spacecraft to incredible speeds over time. Ion thrusters, for instance, use electrically charged particles accelerated by electric fields to generate a small but continuous thrust. While their immediate thrust is low, they offer much higher fuel efficiency than chemical rockets, making them ideal for long-duration robotic missions, where speed builds over months or years, steadily pushing a spacecraft across vast distances. They are like efficient, tireless cosmic sailboats. Research is also intensely focused on nuclear thermal propulsion, (NTP). Imagine using the immense heat from a nuclear reactor to superheat a propellant, expelling it at extremely high velocities to generate thrust. NTP promises a much higher thrust-to-weight ratio than current chemical rockets, and critically, a much higher exhaust velocity, which translates directly into drastically reduced transit times to distant celestial bodies. This technology could cut the travel time to Mars from many months to just a few weeks or a couple of months, making human missions far more feasible and safer. By reducing exposure to radiation and the psychological strains of long confinement, it's like building a cosmic bullet train. Beyond these, even more theoretical concepts are explored. Solar sails, for example, harness the tiny but continuous pressure of photons from the sun, or powerful lasers, to propel a spacecraft, much like a sailboat, uses wind. These offer a fuelless, incredibly long-duration propulsion method ideal for future interstellar probes. Moreover, the ability to launch heavier payloads and conduct more frequent missions due to reduced costs and increased efficiency could vastly expand our capabilities in space. Imagine building large-scale infrastructure in orbit, constructing advanced telescopes in deep space, or enabling detailed, comprehensive exploration of the outer solar system and even interstellar space. As these advanced propulsion technologies continue to evolve, they might not only make the cosmos more accessible, but also open new horizons in our understanding of the universe and our place within it, heralding a new era of discovery, adventure, and even sustained human presence among the stars. It's a quiet promise, a gentle hum of future journeys, inviting us to dream of horizons yet unseen. And so our gentle cosmic journey comes to a close. We have drifted from the familiar comfort of our blue Earth, out through the swirling wonders of our solar system, and into the grand, mysterious embrace of the Milky Way. We have pondered the fiery lives of stars, the vast tapestry of the cosmic web, and the profound questions of the universe's beginning and end. We've even dared to touch upon the shimmering edges of theoretical physics and whispered about the future of humanity's reach for the stars. As you drift now towards sleep, remember the vastness, the complexity, and the enduring beauty of it all. Remember that even in the deepest mysteries, there is a profound sense of peace and wonder. The universe does not always offer easy answers, but in its boundless questions, it offers an endless invitation to curiosity, to humility, and to a quiet sense of belonging. You are a part of this grand story, a tiny precious spark of consciousness reflecting the light of billions of stars. May your dreams be filled with cosmic dust and starlight, with the silent hum of distant galaxies and the gentle whisper of infinite possibilities. Rest now, curious mind, and know that the universe in all its silent majesty holds countless more wonders for us to ponder another time.